It lies hidden in the constellation of the Swan, a silent predator devouring its companion star, warping space itself, and flooding the cosmos with invisible waves of energy. Cygnus X-1 was once just a flicker of X-rays in the sky. Today, it's one of the most mysterious and terrifying objects we've ever discovered. It's not just a black hole, it's the black hole that proved they were real. But the closer we look, the stranger it gets. What is Cygnus X-1 really hiding? And why does it defy everything we thought we knew about the universe? Let's journey to the edge of physics, and stare into the heart of darkness. But before we continue, subscribe to the channel so you don't miss out on any of these videos. Let's take a deep dive into the black heart of Cygnus X-1. When the first X-ray telescopes began scanning the skies in the early 1960s, astronomers had no idea they were about to stumble across a cosmic juggernaut. The tale begins not with Cygnus X-1's discovery, but with humanity's quest to see beyond the visible, to observe the sky in a different light. Traditional astronomy focused on visible wavelengths, the kind our eyes can see. But the universe speaks in many voices, and X-rays are among the most energetic of them all. In 1964, using sounding rockets launched high into the atmosphere, scientists began detecting intense X-ray emissions from seemingly empty regions of space. One such source was detected in the Cygnus constellation, and it was dubbed Cygnus X-1, the first X-ray source found in that region. At first, it was just a name, a coordinate, a point of light invisible to the naked eye but screaming in the high-energy spectrum. It didn't take long for astronomers to realize that something extraordinary was going on. The X-ray emissions weren't steady. They fluctuated wildly, sometimes pulsing, sometimes vanishing and reappearing. This wasn't a simple star, or a galaxy, or any typical cosmic object. This was something different. Something exotic. To understand what made Cygnus X-1 so special, we need to talk about stellar evolution. Stars are not eternal. They are born, they live, and they die. And when the most massive stars die, they don't fade away quietly. They explode in titanic supernovae, leaving behind dense remnants. For small stars like our Sun, that remnant is a white dwarf. For heavier stars, it's a neutron star, an object so dense a teaspoon of it would weigh billions of tons. But for the most massive stars of all, those with cores many times the mass of the Sun, even a neutron star isn't dense enough. Gravity continues to collapse the core until it becomes a singularity, a black hole. In the mid-20th century, black holes were still largely theoretical. Based on Einstein's theory of general relativity, they were mathematical curiosities, fascinating but unproven. No one had actually seen one, or found definitive proof that they existed. Cygnus X-1 changed all that. One of the early clues came from the behavior of the X-ray emissions. Black holes themselves don't emit light, but when they're feeding, devouring nearby matter, they can become some of the brightest objects in the universe. Matter falling into a black hole forms an accretion disk, spinning faster and faster as it spirals inward, heating up due to friction until it emits vast amounts of X-rays. Cygnus X-1 was doing exactly that. But astronomers needed more evidence. They needed to know what was feeding it. In the 1970s, Cygnus X-1 was studied more closely, particularly with optical telescopes. Astronomers identified a companion star, a massive blue supergiant named HD 226868. This star was orbiting an unseen companion in a tight 5.6-day orbit. The mass of this hidden object, inferred from the motion of HD 226868, was too large to be anything but a black hole. It wasn't just that it was heavy, it was too heavy. Heavier than any known neutron star. Too heavy to be explained away. This was it. The smoking gun. The implications were enormous. For the first time, scientists had a candidate for a real, bona fide black hole. Cygnus X-1 became the poster child of black hole studies, the first object widely accepted as a stellar mass black hole. It cemented the reality of black holes not just as mathematical constructs, but as physical objects in the universe. But we're just scratching the surface. Cygnus X-1 lies about 6,070 light-years away from Earth, close by galactic standards, and it's nestled in the Cygnus constellation, also known as the Northern Cross. The black hole itself is believed to have a mass of around 21 solar masses, meaning it weighs about 21 times as much as our Sun. Its companion star, HD 226868, is no slouch either. It's an O-type supergiant, roughly 40 times the mass of the Sun and tens of thousands of times more luminous. This binary system is one of the most well-studied pairs in all of astronomy. Now, let's visualize the system in detail. The black hole and its massive companion orbit a common center of mass, locked in an eternal dance. The gravitational pull of the black hole is so strong that it's stripping material from the outer layers of the supergiant star. This material forms a stream, falling inward toward the black hole, heating up dramatically, and forming the accretion disk. The disk glows brightly in X-rays, but it also generates complex jets, beams of particles ejected at near light speeds perpendicular to the disk. These jets interact with the interstellar medium, creating shock waves, radiation, and possibly even affecting star formation in the region. This process is violent, chaotic, and incredibly energetic. It's also variable. The brightness of Cygnus X-1 changes on timescales of seconds, hours, and days. This variability gives us vital clues about the size and behavior of the accretion disk. Since changes in brightness can only travel at the speed of light, rapid fluctuations imply a compact emission region, exactly what we'd expect from a black hole. In 1990, the High Energy Astrophysics Observatory, HEO1, provided detailed spectral data, confirming that Cygnus X-1's X-rays followed a pattern consistent with Compton scattering in a hot corona of electrons surrounding the accretion disk. This was more evidence of a black hole, as such a structure is a hallmark of these exotic objects. Later missions like RxD, Rossi X-ray Timing Explorer, and Chandra X-ray Observatory continued the observations, revealing even more complexity. Even more astonishingly, recent measurements using Very Long Baseline Interferometry, VLBI, have allowed astronomers to measure the spin of Cygnus X-1's black hole. Yes, black holes can spin, and this one is spinning fast. In fact, it may be spinning at nearly the maximum rate allowed by physics, a dizzying velocity that drags spacetime around with it due to an effect called frame dragging. This intense spin may influence the shape and behavior of the accretion disk and jets, and it provides a fascinating testing ground for general relativity. Cygnus X-1 is more than just a cosmic oddity. It is a laboratory for physics under extreme conditions. Every photon emitted from the system tells us something about matter, energy, gravity, and the fabric of the universe. We have studied it in infrared, ultraviolet, optical, X-ray, and gamma-ray light. It's a beacon not of light, but of knowledge. And yet, for all we've learned, questions remain. Was Cygnus X-1 born as a black hole, or did it form in a supernova? If it did explode, why didn't we detect a remnant or a surrounding nebula? Some astronomers believe that Cygnus X-1 might have formed via direct collapse, a process where a massive star collapses into a black hole without an explosion. If true, this has implications for how black holes form across the cosmos. There's also the mystery of how such a massive black hole ended up in a binary system with a massive star. Did it form with the star? Did it capture the star later? Did they both form from the same molecular cloud? Each of these questions leads to more layers of complexity in our understanding of stellar evolution. And what of the future? HD 226868 is still burning bright, but stars that massive don't live long. In a few million years, it too will end its life, potentially as another black hole. When that happens, we might be left with a binary black hole system, two black holes orbiting each other in a death spiral, gradually losing energy through gravitational waves until they merge in a colossal burst of energy that could be detected across the cosmos. What's even more mind-bending is that we've already started detecting such black hole mergers with instruments like LIGO and Virgo. The data from Cygnus X-1 may help us better understand these signals, the final roars of colliding black holes. But before we rush to the future, we must linger here, in the glow of Cygnus X-1's mystery. There's more to uncover, much more. The story of Cygnus X-1 would take yet another dramatic turn as the decades progressed and astronomers began to uncover not just its isolated behaviors, but also its role in influencing its surroundings. The accretion disk around Cygnus X-1, the very structure that provides the immense energy observed in X-rays, became the focus of theoretical and computational astrophysics. Its structure was found to be extraordinarily dynamic, exhibiting both chaotic turbulence and periodic behavior. The viscous heating of the disk due to gravitational shear created extremely high-energy environments, making Cygnus X-1 one of the hottest X-ray sources ever observed. The intense X-ray radiation, it turns out, does not come solely from the inner disk. Observations by high-resolution X-ray spectrometers revealed a phenomenon known as the corona, a cloud of superheated electrons above the accretion disk that upscatter photons to higher energies. These coronae are believed to be the result of magnetic reconnection events, similar in spirit to solar flares but occurring in environments millions of times more energetic. The corona of Cygnus X-1 extends beyond the inner rim of the disk and adds to the total luminosity of the system. It is in this region that general relativistic effects are most pronounced. Photons emitted from near the event horizon are stretched, bent, and sometimes trapped by the enormous gravitational field. This distortion gives astronomers a unique laboratory to test Einstein's predictions. In Cygnus X-1, such gravitational lensing effects were observed, as were iron line emissions that had been relativistically broadened and redshifted. These spectral distortions tell us not only that we are observing emissions from a relativistic environment, but also allow scientists to infer properties of the black hole itself, including its spin. The spin of Cygnus X-1, in fact, became a major area of investigation. A black hole's spin is a crucial parameter. It dictates how spacetime is twisted around it and determines the innermost stable orbit for matter in the accretion disk. Through the use of spectral fitting methods and quasi-periodic oscillations, it was eventually concluded that Cygnus X-1 is spinning at nearly the maximum rate allowed by general relativity. This finding had profound implications. A maximally spinning black hole could only have attained such momentum through an extraordinary collapse of a massive, rapidly rotating progenitor star or through the accumulation of angular momentum via accretion over millions of years. But there's more to Cygnus X-1 than just its core mechanics. The companion star, HD 226868, plays a massive role in the dynamics of the system. With a mass estimated between 20 and 40 times that of the Sun, this O-type supergiant not only feeds the black hole, but also emits a stellar wind that is both powerful and complex. These stellar winds are composed of charged particles accelerated by radiation pressure from the star's outer layers. The interplay between the black hole's gravity and the star's wind creates a dynamic environment rich in particle interactions, shock waves, and magnetic field distortions. As matter is stripped from HD 226868, it does not fall into the black hole directly. Instead, the angular momentum of the gas causes it to spiral inward, forming the accretion disk. The magnetic fields within this disk twist and rotate, occasionally becoming so tangled that they break and reconnect, releasing bursts of X-ray radiation. This phenomenon creates variability in the X-ray output of Cygnus X-1, which has been recorded in thousands of datasets over the years. Variability timescales range from milliseconds to days, offering a detailed picture of the processes happening near the event horizon. Cygnus X-1's variability is so complex that it has become a benchmark for studying accretion physics and black hole binaries. Using Fourier analysis and autocorrelation techniques, astronomers have parsed this variability into distinct components: flickering noise, quasi-periodic oscillations, QPOs, and high-frequency turbulence. Each of these components provides a glimpse into the underlying mechanisms of the accretion disk and the space-time geometry around the black hole. Quasi-periodic oscillations, in particular, are of enormous interest. They represent semi-coherent fluctuations in the X-ray output, and they occur at frequencies that appear to correlate with the orbital velocities of matter in the inner disk. In Cygnus X-1, QPOs have been observed at frequencies corresponding to a few hertz, suggesting that they originate from regions mere tens of kilometers from the event horizon. The existence and behavior of QPOs have led to many theoretical models, some invoking resonance phenomena between orbital motion and disk oscillations, others pointing to magnetorotational instabilities or discoseismic modes. One of the more fascinating findings related to Cygnus X-1 is the existence of relativistic jets. Though more prominent in other types of black holes like quasars and microquasars, Cygnus X-1 has shown evidence of launching narrow beams of particles at nearly the speed of light. These jets, aligned with the black hole's rotational axis, are thought to be powered by the twisting of magnetic fields anchored in the inner accretion disk. The Blandford's-Najek mechanism, a theoretical framework proposed in the 1970s, offers a compelling explanation. It suggests that energy can be extracted from a spinning black hole via magnetic fields, converting rotational energy into collimated outflows. Observations of radio emissions from Cygnus X-1 confirmed the presence of these jets, albeit on a more modest scale compared to larger systems. The Very Long Baseline Array, VLBA, detected elongated radio lobes extending from the central system, confirming the presence of relativistic jets. These jets, while smaller than those in distant quasars, provide direct evidence that stellar mass black holes operate on the same fundamental principles as their supermassive counterparts. In addition to being a cosmic laboratory for studying gravity and quantum effects near black holes, Cygnus X-1 is also a critical piece of the puzzle in understanding stellar evolution. The very existence of a massive black hole in a binary system with an O-type star raises profound questions. How did such a system form? How did the black hole avoid disrupting or absorbing its companion during formation? What does this tell us about the life cycle of massive stars? The leading theory suggests that the progenitor of Cygnus X-1's black hole was a star even more massive than HD 226868. During its life, this progenitor would have burned through its nuclear fuel quickly, expanding into a red supergiant before undergoing gravitational collapse. However, unlike typical supernovae that eject massive amounts of matter, Cygnus X-1's progenitor may have undergone a direct collapse into a black hole. This process would have produced little to no explosion, allowing the binary system to remain gravitationally bound and giving rise to a black hole of immense mass. This direct collapse hypothesis has implications for gravitational wave astronomy. It suggests that many massive stars might collapse quietly into black holes, without the telltale signs of a supernova. As gravitational wave detectors like LIGO and Virgo continue to uncover black hole mergers, models of stellar evolution are being refined, and Cygnus X-1 remains a key anchor point for these models. Moreover, Cygnus X-1's relatively close distance, about 6,000 light-years from Earth, provides a unique advantage. It allows astronomers to make detailed measurements not possible with more distant sources. For example, parallax measurements from the Very Long Baseline Array help refine the system's distance, and Gaia data has improved our understanding of its proper motion through space. These data points feed directly into calculations of mass, luminosity, and orbital dynamics. As science has evolved, so too has our ability to simulate systems like Cygnus X-1. Supercomputers running magnetohydrodynamic simulations now model the entire accretion process, from stellar wind capture to jet formation. These simulations incorporate Einstein's equations for general relativity, complex plasma physics, and nuclear processes. They predict the shape of the accretion disk, the structure of the corona, and the properties of relativistic jets. The fact that these simulations match observational data so well is a testament to how far the field has come, and how instrumental Cygnus X-1 has been in shaping that progress. And yet, despite decades of research, Cygnus X-1 still holds mysteries. Questions remain about its long-term evolution. Will it eventually consume its companion star? Will the binary orbit tighten as gravitational radiation causes orbital decay, leading to a black hole neutron star merger or black hole system? How long will the accretion process continue, and how will it change the black hole's mass and spin? We also continue to search for evidence of exotic physics. Some scientists have proposed that the inner edge of the accretion disk might exhibit quantum gravitational effects. Others wonder whether dark matter interacts in any meaningful way near such extreme objects. Could Cygnus X-1 be a gateway to understanding the unification of general relativity and quantum mechanics? As we peer deeper into the cosmos and push our instruments to their limits, Cygnus X-1 stands as a silent sentinel, both an ancient relic of stellar death and a blazing engine of high-energy physics. Black holes are often described as the end of the road for matter, a one-way trip into darkness, but Cygnus X-1 defies that notion by being a luminous paradox. It is one of the brightest X-ray sources in our galaxy, visible not in the traditional sense of light, but through the violent radiation it emits as matter spirals into oblivion. The brilliance of this system comes not from the black hole itself, which by definition emits no light, but from the fury of infall, the extreme energy released as stellar material accelerates to near-light speed before crossing the event horizon. The energy from Cygnus X-1 also extends beyond the X-ray spectrum. Observations in ultraviolet, optical, infrared, and radio wavelengths reveal the complex interactions between the black hole and its companion star. As the supergiant loses mass via stellar wind, it creates a stream of charged particles that are gravitationally attracted to the black hole. However, the path of this material is not linear. The black hole's intense gravitational pull stretches the material into a spiraling disk. As this matter moves inward, the friction and compression raise the temperature to millions of degrees, emitting intense radiation in the process. But not all of the matter makes it across the event horizon. Some of it is redirected by magnetic and centrifugal forces, flung away in polar jets that extend for thousands of kilometers. These jets, though comparatively small by extragalactic standards, are no less dramatic. They demonstrate the enormous influence black holes exert on their environment, not just in drawing material in, but in ejecting it out with tremendous force. These jets are often seen in the radio spectrum, where the high-speed electrons emit synchrotron radiation as they spiral through magnetic fields. These jets and emissions aren't just random bursts. They follow a rhythm, a symphony dictated by gravity, magnetism, and momentum. Cygnus X-1 shifts between high and low energy states, known as hard and soft states. In the hard state, the emission is dominated by high-energy X-rays from the corona, and the jets are typically stronger and more defined. In the soft state, the inner accretion disk becomes more visible, emitting lower-energy X-rays, and the jets often diminish or disappear. These state changes can happen over days, weeks, or months, and studying them has given scientists insight into the physics of accretion and jet production. The states of Cygnus X-1 are not simply a curiosity. They represent fundamental changes in how energy is transported and released in the system. The transition between states may be tied to instabilities in the accretion disk, fluctuations in mass transfer from the companion star, or even magnetic cycles. What is clear is that Cygnus X-1 is not a static object. It evolves, pulsates, flickers. It is alive with motion and transformation, each change revealing another layer of complexity. Even the event horizon of Cygnus X-1, though invisible, plays a critical role in shaping what we observe. Matter disappearing past the event horizon leaves behind telltale signatures. These include the disappearance of emission lines, the cessation of certain variability patterns, and the gravitational redshift of photons escaping from near the edge. These effects are subtle but powerful. They allow us to infer the presence of the event horizon itself, an otherwise intangible surface. Cygnus X-1 also serves as a testing ground for alternate theories of gravity. While general relativity predicts the behavior of spacetime around black holes with exquisite precision, physicists have long sought ways to probe its limits. Some theories suggest modifications to gravity on very small or very large scales, while others propose entirely new frameworks. By analyzing the motion of matter around Cygnus X-1, the timing of X-ray bursts, and the spectral shifts in emitted radiation, researchers can test these theories under the most extreme conditions nature offers. One of the most groundbreaking confirmations that Cygnus X-1 contains a black hole came in the 2010s, when a team of astronomers used precise astrometric and spectroscopic measurements to determine the mass of the unseen companion. The resulting figure, around 21 solar masses, was far too great to be a neutron star or any other known compact object. This measurement, combined with the absence of surface emissions and the presence of an accretion disk, left no doubt Cygnus X-1 harbors a true black hole. This mass measurement also provided insights into how black holes form. It suggested that the progenitor star of Cygnus X-1 must have been extraordinarily massive, likely over 40 solar masses before it collapsed. Moreover, the fact that it did not expel its companion in a supernova explosion implied that the collapse was nearly silent, a rare, direct collapse into a black hole without a disruptive explosion. This realization upended long-held assumptions and prompted new studies into the final stages of stellar evolution. Cygnus X-1's companion star, AD226868, is itself a marvel. With a surface temperature exceeding 30,000 Kelvin, it shines tens of thousands of times more brightly than our Sun. The sheer scale and power of this star create a stellar wind so intense that it can strip its own outer layers and feed them into the gravitational maw of the black hole. The interaction between the star's radiation and the gravitational pull of the black hole creates a complex, ever-changing interface, a boundary where matter is stretched, ionized, and drawn into spirals of death. This interaction zone also emits its own radiation. As particles collide and decelerate, they produce a spectrum of emissions that allows scientists to map the density and composition of the wind. Spectroscopic analysis shows lines of highly ionized iron, calcium, and other elements, each distorted by the motion and temperature of the surrounding gas. These lines act like fingerprints, offering clues about the physical conditions near the black hole. Because the companion star orbits the black hole every 5.6 days, it presents varying angles for observation. This orbital motion allows astronomers to study the system in exquisite detail, examining how light is absorbed and re-emitted by the gas surrounding the black hole. These observations have led to models of the wind's structure, how it funnels toward the black hole, how it forms shock waves, and how it evolves over time. Cygnus X-1 is also a key system for understanding the formation of binary black holes. As gravitational wave observatories detect more black hole mergers, the question arises: how do such pairs form and evolve? Cygnus X-1 offers a possible pathway. A massive binary system undergoes one collapse, forming a black hole. The companion may then evolve into a second black hole, setting the stage for a future merger. The timescales involved are immense, but in a galaxy teeming with stars, such events are inevitable. Cygnus X-1 could represent the early stages of one such evolutionary path. The future of Cygnus X-1 is a matter of both observation and speculation. Over millions of years, the companion star will lose more and more mass. Eventually, it may explode as a supernova or collapse directly into another black hole. If the system remains gravitationally bound, it will become a binary black hole system. Such systems are the very ones that LIGO and other detectors have observed, merging in spectacular events that send ripples across space-time. The ongoing observation of Cygnus X-1 remains a top priority for high-energy astrophysics. New instruments, such as the James Webb Space Telescope, upcoming X-ray observatories, and next-generation radio arrays, will offer unprecedented resolution and sensitivity. These tools will allow astronomers to probe even closer to the event horizon, to study the fine structure of the accretion disk, to detect the polarization of X-rays as they twist through warped spacetime. Each new observation adds another brushstroke to the portrait of Cygnus X-1. It is a system of extremes: immense gravity, furious radiation, and relentless change. It offers a glimpse into the processes that shape galaxies, govern stellar death, and challenge our understanding of fundamental physics. Cygnus X-1 is not just a black hole, it is a cosmic monument, carved not in stone, but in light, gravity, and time. The influence of Cygnus X-1 goes far beyond the confines of its own binary system. It has, in many ways, shaped our broader comprehension of how black holes behave, evolve, and interact with their surroundings. For decades, it has served as a beacon, an astrophysical Rosetta Stone that deciphers the chaotic symphony of black hole dynamics. And unlike many theoretical black holes or distant quasars that lie at the heart of galaxies, Cygnus X-1 is close enough, just over 6,000 light-years, to observe in extraordinary detail. This proximity has made it a kind of laboratory for space-time physics, a rare environment where the edges of Einstein's general relativity meet the frontiers of quantum theory and high-energy astrophysics. Cygnus X-1 has helped redefine how scientists conceptualize the life cycles of stars. Massive stars like the progenitor of the Cygnus X-1 black hole don't fade gently. They meet their fate in some of the most energetic events in the cosmos. However, in the case of Cygnus X-1, that final collapse didn't light up the sky. It didn't become a spectacular supernova. Instead, it vanished silently, collapsing directly into a black hole without an explosion. This kind of collapse suggests that some stars are so massive and so tightly bound by gravity that their cores collapse inward before any outward shockwave can form, leaving no brilliant remnant behind, only darkness. Such an outcome redefines expectations about the deaths of stars and the mechanisms of black hole formation. It raises new questions. How often does direct collapse occur? What determines whether a star explodes or implodes? And what does this mean for the number of black holes quietly drifting through our galaxy, unseen, undetected, and perhaps far more numerous than once believed? Further deepening the mystery is the incredible spin of the black hole in Cygnus X-1. Measurements have shown that this black hole is spinning near the theoretical maximum, very close to the speed of light. Such a high spin suggests that the black hole either formed with this rotation or has been spun up over time by the accretion of matter from its companion. The spin rate isn't just an incidental statistic, it dramatically affects the shape of the black hole's event horizon and the dynamics of the accretion disk. A faster spin means the inner edge of the accretion disk can sit closer to the event horizon, allowing even more gravitational energy to be converted into radiation. This process likely fuels some of the intense X-ray emission we see from Cygnus X-1. And the way that matter behaves in this violent regime, just above the event horizon, touches on the edge of physics as we know it. Here, the gravitational field is so intense that time itself slows to a crawl, and space curves dramatically inward. Photons emitted from this region are redshifted by the time they reach Earth, losing energy as they escape the grip of the black hole. This redshift offers scientists clues about the space-time curvature near the event horizon, turning observations into indirect measurements of one of the most mysterious objects in existence. Cygnus X-1 is also crucial in the study of accretion, the process by which matter collects around compact objects like black holes and neutron stars. Accretion is not just an incidental process, it is the main mechanism by which black holes interact with the universe. And in the case of Cygnus X-1, accretion is spectacularly active. The material from the companion star doesn't fall in all at once, it spirals inward in a flattened disk, heating up due to internal friction, emitting radiation, and revealing the physical processes governing angular momentum, viscosity, magnetism, and turbulence. This accretion disk also exhibits quasi-periodic oscillations, flickering at frequencies that may reflect orbital movements close to the event horizon or the wobbling of the inner disk. These oscillations aren't random, they are windows into the physics near the black hole. Scientists can use them to infer the geometry of the disk, the spin of the black hole, and the nature of gravity itself in extreme regimes. The black hole also likely possesses a corona, a region of superheated plasma above and below the accretion disk that emits X-rays. The origin and structure of this corona are still under study, but one theory suggests that it is maintained by magnetic reconnection events, similar to solar flares on our Sun, but vastly more powerful. The X-rays emitted by this corona sometimes reflect off the accretion disk, creating a distinctive spectral feature known as the iron K-alpha line. This line is often broadened and skewed due to relativistic effects, further reinforcing that what we are seeing is occurring in the immediate vicinity of the event horizon. The iron line is not just a marker of composition, it's a diagnostic tool. Its shape and width tell us how fast the accretion disk is spinning, how close it gets to the black hole, and how much the emitted light is being warped by gravity. Such subtle measurements allow scientists to reverse engineer the dynamics of black holes, not through direct contact, but by reading the light like a code. And then there's the broader role that Cygnus X-1 plays in galactic ecology. Black holes are often thought of as isolated destroyers, but in reality, they can influence star formation, drive chemical evolution, and inject energy into the interstellar medium. The radiation and jets from Cygnus X-1 are energetic enough to heat nearby gas clouds, possibly compressing them into new star-forming regions or dispersing them entirely. These effects ripple outwards, shaping the structure of the galaxy on scales far larger than the black hole itself. Even gravitational waves, ripples in the fabric of spacetime, enter the story of Cygnus X-1. Though the system is not yet producing detectable gravitational waves, it provides a possible evolutionary path toward future black hole mergers. If the companion star eventually collapses into another black hole, the pair would slowly spiral inward over billions of years, releasing gravitational radiation. When they finally merge, the resulting shockwave could be detected by observatories like LIGO and Virgo, confirming predictions made today based on systems like Cygnus X-1. In this way, Cygnus X-1 connects many domains of astrophysics, stellar evolution, high-energy physics, general relativity, and cosmology. It is more than a black hole, it is a touchstone for some of the deepest questions we can ask about the universe. Why do stars live and die the way they do? What lies at the edge of space and time? Can we understand matter under the most extreme conditions imaginable? Our ability to explore Cygnus X-1 has also evolved in tandem with technology. Early discoveries were limited to simple X-ray counts and crude spectral measurements. But today, astronomers employ a suite of advanced telescopes, such as NASA's Chandra X-ray Observatory, ESA's XMM Newton, and even radio interferometers like the Very Long Baseline Array. These tools work together to paint a rich, dynamic picture of the system, its structure, evolution, and variability. In the coming decades, even more powerful instruments will come online, such as the Lynx X-ray Observatory and the European Athena mission. These will bring higher resolution, faster response times, and better spectral sensitivity. They will enable scientists to study fluctuations in X-ray brightness on millisecond timescales, to track the orbital dynamics of the companion star with greater precision, and perhaps to image the shadow of the black hole itself, though that remains a challenging task due to its relatively small size and greater distance compared to the supermassive black hole in M87. But whether or not we ever directly image Cygnus X-1's event horizon, the wealth of data already gathered confirms that this system is a true celestial gem. Its very existence challenges what we thought we knew about the universe, forces us to refine our theories, and compels us to look deeper into the cosmic night. For every answer it has provided, it has raised a dozen new questions. And that is the hallmark of a truly profound discovery. The motion of Cygnus X-1 through our galaxy offers another fascinating dimension to its story. As with all objects bound by the Milky Way's gravitational field, Cygnus X-1 is not stationary, it is on the move. But what makes its motion particularly intriguing is the revelation that it hasn't received a powerful kick, as would typically be expected from a supernova explosion. When massive stars die in supernovae, the asymmetric blast often imparts a substantial velocity to the resulting neutron star or black hole, sometimes flinging it across space at hundreds of kilometers per second. However, Cygnus X-1 shows no sign of such a violent ejection. Instead, the system appears to have remained relatively stationary, continuing to orbit within the galaxy in a manner similar to its prior trajectory. This observation offers indirect evidence that the black hole was formed via direct collapse, an implosion rather than an explosion, where the progenitor star's mass collapsed inward so rapidly and symmetrically that no significant outward force was released to propel the black hole. It's an eerie thought, a star so massive and so gravitationally bound that it essentially vanished without a trace of light or fury, leaving behind only darkness and X-rays as its legacy. From a theoretical standpoint, this quiet transformation has enormous implications. It supports the idea that the most massive stars in the universe may often skip the brilliant supernova stage altogether. This changes how we calculate the chemical enrichment of galaxies, how we estimate supernova rates, and how we account for the formation and distribution of black holes. If many black holes form silently, then there may be vast numbers of them drifting undetected through space, influencing their environments invisibly. Cygnus X-1's mass, too, has refined our understanding of the upper limits of stellar black holes. Originally believed to be around 15 solar masses, Recent studies have revised this estimate upward to over 20 solar masses. That makes Cygnus X-1 one of the most massive stellar mass black holes known in the Milky Way. And that's significant, because for many years, astrophysicists puzzled over why there seemed to be a gap between the largest neutron stars and the smallest black holes, known as the mass gap. Neutron stars are believed to max out around 2.5 to 3 solar masses before collapsing into black holes, yet early surveys found few black holes below 5 solar masses. Cygnus X-1 helps fill in that upper end of the scale, demonstrating that massive black holes can form from individual stars without requiring merger events or exotic circumstances. The optical star in the system, HD 226868, also plays a critical role. Classified as a blue supergiant, it has a mass around 40 times that of the Sun and emits intense stellar winds. These winds not only fuel the black hole's accretion disk but also offer insight into the mass loss and evolution of massive stars. By observing the variability in the star's brightness, spectrum, and emission lines, scientists can track how matter is stripped away by the black hole, measure the strength and orientation of magnetic fields, and model how radiation pressure affects the wind's structure. Interestingly, HD 226868 doesn't just sit passively in orbit. It's being distorted by the gravity of the black hole. Its outer layers bulge slightly in the direction of the black hole, pulled into a teardrop shape as it approaches Roche lobe overflow. This interaction creates complex gravitational tides that affect the transfer of angular momentum, shape the accretion disk's behavior, and can even cause precession in the orbit itself. Such distortions aren't just theoretical. They can be seen in the light curves of the star and modeled in simulations to reconstruct the three-dimensional structure of the system. X-ray observations reveal additional layers of complexity. The emission isn't constant, it fluctuates wildly, sometimes brightening suddenly in bursts, other times dimming inexplicably. These variations are due to changes in the density and structure of the stellar wind, the motion of infalling gas, and occasional clumps or instabilities in the accretion disk. In some cases, flares occur due to magnetic reconnection events, where magnetic field lines in the disk snap and realign, releasing bursts of energy not unlike solar flares but on a vastly greater scale. At times, astronomers have observed dips in the X-ray output that correlate with the orbital period, suggesting that part of the accretion disk is occasionally obscured by denser regions in the stellar wind or by warped portions of the disk itself. These dips provide clues about the geometry of the system, allowing scientists to model the vertical thickness of the disk and how its orientation shifts over time. Then there are the relativistic effects. Close to the event horizon, space-time becomes so distorted that time slows down significantly, a phenomenon predicted by Einstein's general relativity. If you could hover just outside the event horizon of Cygnus X-1 and observe the universe, you'd see time in the outside world speed up dramatically. Conversely, a distant observer looking in would see processes near the event horizon unfold in slow motion. These time dilation effects subtly influence the timing of observed X-ray emissions, requiring relativistic corrections to fully interpret the data. Even the energy of the emitted photons is altered by the black hole's gravity. As photons climb out of the gravitational well, they lose energy and are redshifted, stretched into longer wavelengths. This gravitational redshift changes the observed spectra, and by carefully measuring it, scientists can infer the strength of the gravitational field and the depth of the potential well surrounding the black hole. Such measurements help constrain the radius of the innermost stable circular orbit, ISCO, a key boundary in black hole physics that varies depending on the black hole's mass and spin. Cygnus X-1 is also a cornerstone in the study of black hole jets. While its jets are not as powerful or well-defined as those of some other black holes, there is evidence of weak, steady outflows perpendicular to the accretion disk. These jets may be powered by magnetic fields twisted by the rotating disk and black hole, forming a kind of cosmic dynamo that channels particles outward at nearly the speed of light. The physics of these jets touches on one of the greatest mysteries in astrophysics: how energy can be extracted from a black hole's spin, a process described by the Blandford-Snejek mechanism. This mechanism suggests that black holes with strong magnetic fields and rapid spin can tap into their rotational energy to power jets, effectively converting gravitational and rotational energy into kinetic energy. If true, this would mean that Cygnus X-1 is not just a passive consumer of matter, but an active generator of cosmic structure, launching beams of plasma that may influence nearby star formation, regulate the interstellar medium, and even play a role in galaxy evolution. In modeling these processes, scientists use numerical simulations that combine general relativity, magnetohydrodynamics, MHD, and radiation transport. These simulations require massive computational power and help visualize how matter swirls, heats, fragments, and either falls into the black hole or escapes in a jet. Cygnus X-1 provides a critical testbed for validating these models, as its relatively nearby distance allows observations of high precision. But perhaps one of the most profound contributions of Cygnus X-1 is how it has shaped our cultural and philosophical understanding of the universe. It has appeared in music, literature, and film, serving as a symbol of the mysterious, the unknowable, and the awe-inspiring forces that lie beyond human comprehension. The Canadian rock band Rush famously dedicated a two-part epic to Cygnus X-1 in the late 1970s, weaving it into a science fiction narrative of space travel and transformation. For many, the black hole has become a metaphor for the unknown, an object that defies understanding yet draws us in with irresistible curiosity. And that curiosity continues to grow. As we refine our observational tools and deepen our theoretical frameworks, Cygnus X-1 remains a lighthouse in the night, a fixed point from which we navigate the dark seas of cosmic understanding. Every photon it emits carries with it the signature of extremes, of gravity stretched to its limits, of matter pushed to its breaking point, and of space and time curved so sharply that they nearly fold in on themselves. In this sense, Cygnus X-1 is more than just an object in the sky. It is a challenge, a puzzle set by the cosmos itself, inviting us to look deeper, think harder, and reach farther into the night. It reminds us that even in the deepest darkness, there is light, not from the object itself, but from what it reveals about the universe we inhabit. Even more fascinating is how Cygnus X-1 challenges our models of binary evolution. Binary star systems are remarkably common in the universe. Many, if not most, stars form in pairs or groups. But the evolution of such systems, especially when one member becomes a compact object like a black hole, is notoriously complex. The gravitational interplay between the two stars dictates not just their orbital behavior, but also their internal structures, rotational speeds, and eventual fates. In the case of Cygnus X-1, what we observe is a system that must have survived a particularly tumultuous past, including the violent death of one star and the intense mass exchange that followed. In all likelihood, the progenitor of the black hole in Cygnus X-1 was once the more massive of the two stars. Stellar evolution tells us that more massive stars burn through their nuclear fuel faster, and thus evolve more quickly. So long before the current supergiant HD 226868 reached its present form, the original massive star would have expanded into a red supergiant, possibly transferring mass to its companion in the process. Eventually, it would have collapsed under its own gravity, forming a black hole. If this had happened through a supernova, the energy released might have disrupted the binary system entirely, flinging both objects apart. But as previously discussed, the apparent lack of such a disruption supports the idea of a direct collapse, a quiet death, as far as stellar demises go. The result is a rare configuration, a high-mass X-ray binary where a still massive donor star continues to lose material to a black hole that likely never exploded. This alone makes Cygnus X-1 a sort of laboratory for high-energy astrophysics. How does the infalling matter behave in such extreme conditions? How stable is the mass transfer process? Can instabilities in the accretion flow generate quasi-periodic oscillations, those rhythmic pulses sometimes observed in X-ray binaries that hint at internal disk mechanics or warped space-time geometries? Indeed, Cygnus X-1 has revealed patterns of quasi-periodic oscillations (QPOs) that have become central to black hole timing studies. These subtle variations in X-ray intensity appear to repeat on timescales of milliseconds to seconds and are believed to arise from complex interactions in the innermost regions of the accretion disk. They may be tied to the orbiting clumps of matter spiraling inward, or to vibrations of the entire disk structure as it reacts to gravitational and magnetic forces. These oscillations allow scientists to measure properties that are otherwise invisible, such as the size of the inner accretion disk, the inclination of the system, and even, potentially, the black hole's spin rate. Speaking of spin, Cygnus X-1's black hole is believed to be spinning near the maximum allowed by general relativity. That is, it is a Kerr black hole, named after Roy Kerr, the mathematician who found the exact solution to Einstein's equations for a rotating black hole. A rotating black hole differs from a non-rotating one in profound ways. It drags spacetime around with it, a phenomenon known as frame dragging, or more poetically, the lens-stirring effect. This effect can alter the orientation of the accretion disk, creating warps and precession, and it may even be responsible for the alignment of jets. Measurements of Cygnus X-1's X-ray spectrum, particularly the iron K-alpha line, a spectral feature produced when X-rays irradiate iron atoms in the inner disk, have revealed distortions consistent with extreme Doppler shifts and gravitational redshift. These distortions match theoretical predictions for a disk orbiting very close to the event horizon of a spinning black hole. The closeness of the disk's inner edge suggests that the black hole's spin is indeed high, possibly close to the theoretical limit of a dimensionless spin parameter, of 1. Why does spin matter? Because it determines how much energy a black hole can potentially release. A spinning black hole can, through processes like the Penrose mechanism or Blandford-Snagic effect, tap into its rotational energy to drive jets, heat the disk, and influence its surroundings. In this way, black holes are not merely gravitational sinks. They can be engines, capable of affecting their galactic environment. Cygnus X-1 also helps constrain theories about the end states of massive stars. Traditionally, stellar evolution models predicted that very massive stars might become neutron stars first, only collapsing into black holes later through accretion or merger. But Cygnus X-1 seems to have skipped this intermediate stage, going straight from massive star to black hole. If this is common, it would suggest that our population models need to be adjusted, that perhaps there are far more black holes in the universe than previously thought, and fewer neutron stars at high mass. Even the interstellar environment around Cygnus X-1 offers data. The region is home to complex structures shaped by the stellar winds of HD 226868 and the outflows from the black hole. Observations in radio and infrared wavelengths reveal bow shocks, arcs of gas compressed and heated as the system moves through the interstellar medium. These structures provide a record of past activity, a sort of fossilized footprint of the system's journey through space. Studying them allows astronomers to backtrack the motion of Cygnus X-1, estimate its age, and determine how long it has existed in its current form. Furthermore, as observational technology improves, astronomers continue to revisit Cygnus X-1 with fresh eyes. Instruments like the Chandra X-ray Observatory, NuSTAR, and the Very Long Baseline Array, VLBA, offer increasingly precise measurements of its properties. In one recent campaign, astronomers used parallax, the tiny shift in a star's position as Earth orbits the Sun, to refine Cygnus X-1's distance to about 7,200 light-years. That's relatively close by cosmic standards, and it makes Cygnus X-1 an ideal candidate for long-term study. Its proximity means we can resolve fine details that would be lost in more distant systems, and its brightness ensures a strong signal for a wide range of instruments. There is also growing interest in how Cygnus X-1 relates to gravitational wave astronomy. Although Cygnus X-1 itself isn't expected to merge in the near future, its binary components are too widely spaced. Understanding its dynamics helps inform models of systems that might. The Laser Interferometer Gravitational Wave Observatory, LIGO, and other detectors have opened a new window on the universe, capturing ripples in spacetime from black hole collisions. These collisions likely originate in systems not so different from Cygnus X-1, massive binaries where one or both stars eventually collapse into black holes and spiral inward over billions of years. Cygnus X-1, in this context, is a snapshot of an earlier stage in that evolutionary pathway. Studying it allows scientists to estimate the population of merging black holes, calculate merger rates, and test the predictions of general relativity in strong gravity regimes. It is a living fossil of cosmic dynamics, a system that encapsulates birth, death, and the quiet violence of gravity. Even the metaphysical implications of Cygnus X-1 are striking. It challenges the notion of visibility itself, what it means to observe something that can never be seen directly. The black hole is invisible, by definition, yet its presence is undeniable. It exerts influence, commands attention, and reveals itself only through the reactions of the matter around it. In a way, Cygnus X-1 mirrors the limits of human perception. We can only know it through its impact, only understand it by inference. Yet this has not stopped us from probing its depths. With every passing year, new papers are published, new models tested, and new data gathered. Cygnus X-1 continues to be a beacon for scientists, a crucible where ideas about gravity, quantum mechanics, thermodynamics, and radiation intersect. It reminds us that even in the void, there is structure. Even in silence, there is story. The tale of Cygnus X-1 extends beyond its current state. It stretches back into deep time, into epochs where massive stars danced through their brief but powerful lifetimes. In attempting to reconstruct the origins of Cygnus X-1, scientists have sought to understand not only how the black hole formed, but where it came from, and what kind of stellar ancestry led to such an exotic end. Tracing the life cycle of the progenitor star is not easy, but by analyzing stellar evolution tracks and modeling the binary system's history, astronomers can make educated inferences. The progenitor star of the black hole must have had a mass at least 40 times that of our Sun, possibly even more. Such a star would have been born in a stellar nursery rich in gas and dust, collapsing from a dense region of a molecular cloud. Over just a few million years, a blink on cosmic timescales, it would have exhausted the hydrogen in its core, expanded into a supergiant, and ignited heavier elements like helium, carbon, and oxygen in successive stages of fusion. These advanced burning stages happen incredibly quickly, with elements fusing into heavier and heavier atoms until iron is produced. At that point, fusion can no longer yield energy, and gravity takes over. The core collapses, and if the star is massive enough, as was the case for the progenitor of Cygnus X-1, nothing can halt the collapse. A black hole is born. Interestingly, in this particular case, there seems to be no evidence of a traditional supernova remnant, a cloud of debris expanding into space from the star's explosive death. That supports the theory that the black hole formed via direct collapse, in which the core implodes without an outward explosion. The outer layers of the star may have fallen inward, disappearing with the core into the singularity. This silent death may be more common than we once thought, and Cygnus X-1 is a key piece of that puzzle. But the other half of the binary, the companion star HD 226868, is equally fascinating. It too was likely massive from birth, but slightly less massive than the progenitor black hole. Yet its current mass is still astonishing, around 20 to 40 solar masses, making it one of the most massive stars known to orbit a black hole. It is classified as an 09.7 IAB supergiant, a hot, luminous star nearing the end of its life, with powerful stellar winds blowing material into space at millions of kilometers per hour. These winds are crucial, because they provide the black hole with its diet. As the supergiant sheds mass, some of that material is captured by the black hole's gravitational pull. Not all of it falls straight in. Much of it forms an accretion disk, a hot, swirling structure that glows brightly in X-rays. The inner edge of this disk orbits dangerously close to the black hole's event horizon, moving at speeds near the speed of light and heated to millions of degrees. It is here, in this disk, that much of the radiation we detect from Cygnus X-1 originates. The disk is not a stable, tranquil structure. It experiences shocks, turbulence, and magnetic disruptions. These cause flares and variability in X-ray brightness. In fact, Cygnus X-1 is known for exhibiting different states, periods of time when its X-ray emissions change in energy and intensity. It flips between a low/hard state and a high/soft state, which are thought to represent different accretion regimes. In the low/hard state, the disk is cooler and the X-rays are harder, higher in energy. In the high/soft state, the disk is hotter and denser and emits softer, lower energy X-rays. This state switching is a window into the physics of accretion, which remains one of the most complex problems in astrophysics. Despite decades of study, we still do not fully understand how angular momentum is transferred, how magnetic fields shape the flow, or how energy is dissipated within the disk. Cygnus X-1, being one of the brightest and closest black hole binaries, provides a real-time laboratory for exploring these mysteries. What's more, the system sometimes produces jets, high-speed outflows of matter ejected perpendicular to the accretion disk. These jets can stretch for light years, emitting in radio wavelengths as they interact with surrounding gas. Though not as spectacular as the jets from supermassive black holes at the centers of galaxies, they are nonetheless critical to our understanding of feedback processes, how black holes influence their environments. In Cygnus X-1, the presence of jets, disk winds, and variable radiation all suggest a highly dynamic system. These features don't just affect the immediate surroundings. They can shape the interstellar medium itself, carving out bubbles of ionized gas and leaving a permanent imprint on the galaxy. It's no exaggeration to say that black holes like the one in Cygnus X-1 help sculpt the Milky Way. Another layer of complexity is added when we consider relativistic effects. Near the black hole, space-time is warped to extreme degrees. Light itself follows curved paths, and time behaves strangely. If you could hover near the event horizon, ignoring for a moment the deadly tidal forces, you would experience time more slowly than someone far away. This gravitational time dilation, predicted by Einstein's general relativity, has been indirectly confirmed through observations of accretion phenomena in Cygnus X-1 and other systems. The light we see from the inner disk is affected by gravitational redshift. It loses energy as it climbs out of the black hole's gravity well. This alters the spectrum in subtle but measurable ways. Moreover, the iron K-alpha line, a spectral feature seen in many X-ray binaries, is broadened and skewed in Cygnus X-1 in a way that matches predictions for relativistic effects near a spinning black hole. These observations allow us to probe the space-time geometry around the event horizon, a regime where our classical physics breaks down and quantum gravity must eventually take over. And herein lies one of the most tantalizing aspects of Cygnus X-1. It is not just an astrophysical object, but a natural laboratory for testing fundamental physics. By studying its radiation, we can test the predictions of general relativity in the strong field limit. By modeling its disk and jets, we explore magnetohydrodynamics and plasma physics. By analyzing its history and binary evolution, we refine our models of stellar life cycles. And by examining its behavior over time, we uncover new variables in how black holes grow and affect their companions. Even the cultural impact of Cygnus X-1 has been profound. It was one of the first black holes to become widely known in the public imagination, thanks in part to its dramatic name and the early NASA missions that identified it. Its role in scientific history is monumental. It helped transition black holes from theoretical oddities to observable reality. It inspired not just scientists, but artists, writers, and musicians. One notable example is the progressive rock band Rush, who wrote an entire song suite titled Cygnus X-1, exploring themes of consciousness, space travel, and cosmic unity. And yet, despite all we know, Cygnus X-1 still holds secrets. Its long-term evolution is uncertain. Will the supergiant companion eventually go supernova, possibly forming a neutron star or even another black hole? Could the two objects eventually spiral together and merge, producing a gravitational wave signal detectable across the cosmos? Such a scenario could play out over millions of years, but it's not out of the question. If it happens, the resulting merger would be one of the most energetic events in the galaxy, releasing more energy in a few seconds than all the stars in the Milky Way combined. The potential merger of the Cygnus X-1 black hole and its companion star presents one of the most intriguing future scenarios for this system. If the two objects eventually come into close enough proximity, the immense gravitational forces at play would cause them to spiral toward one another, gradually shedding energy in the form of gravitational radiation. This would cause the orbital period of the system to shorten, bringing the black hole and the supergiant closer and closer, until they merge in a cataclysmic event known as a binary black hole merger. The outcome of such a merger would be a new, larger black hole. This type of event would produce intense gravitational waves, ripples in spacetime itself, that could be detected by future gravitational wave observatories, such as the Laser Interferometer Gravitational Wave Observatory, LIGO, or Virgo. These waves, which carry information about the mass, spin, and other properties of the merging black holes, would offer new insights into the nature of black holes, as well as the fundamental physics of gravity. Since the discovery of gravitational waves from merging black holes in 2015, the detection of such waves has become a key goal for astrophysics, and Cygnus X-1's eventual merger might be a spectacular source of such signals. One fascinating aspect of this system is how it connects to broader questions about the life cycles of stars, stellar mass black holes, and the evolution of galaxies themselves. The story of Cygnus X-1 encapsulates the entire life cycle of a massive star, from its birth in a stellar nursery to its ultimate death as a black hole. This cycle doesn't just end with the formation of a black hole. The interactions between the black hole and its companion continue to shape the environment around them. As the black hole pulls material from its companion, it radiates this material away in the form of X-rays, producing a spectacle visible across great distances. These processes can influence the interstellar medium by injecting energy, possibly triggering new star formation or altering the dynamics of nearby stars and gas clouds. One of the more profound questions raised by Cygnus X-1 and other stellar mass black holes is the process of black hole growth. Black holes are not passive objects, they actively shape their surroundings. Over time, they accumulate mass from their environment. This process of accretion can lead to a black hole growing in size, and potentially becoming a supermassive black hole at the centers of galaxies. In fact, black holes like Cygnus X-1 may offer valuable clues about how smaller black holes evolve into the supermassive black holes that lie at the heart of most galaxies, including our own Milky Way. The comparison between Cygnus X-1 and the supermassive black hole at the center of the Milky Way, Sagittarius A, is enlightening. While Cygnus X-1 is a relatively small black hole, compared to the gargantuan masses of supermassive black holes, it shares many of the same physical properties. Both black holes accrete matter from a companion, produce jets, and distort spacetime in ways that can be studied with advanced observational techniques. However, the processes occurring in Cygnus X-1 are on a much smaller scale, and it provides a laboratory to study how accretion disks, relativistic jets, and gravitational waves might behave in the presence of a black hole of much greater mass. There's another important piece to this puzzle: the role that Cygnus X-1 and other stellar mass black holes may play in the larger-scale structure of the universe. On cosmological scales, black holes are thought to play a role in regulating star formation, controlling the growth of galaxies, and shaping the evolution of cosmic structures. The energy released by the accretion of matter onto black holes can heat up gas in the surrounding galaxy, preventing new stars from forming and even driving gas out of the galaxy. This feedback mechanism has been proposed as one of the key factors in limiting the size of galaxies and in shaping their stellar populations. Cygnus X-1, despite being a relatively small object, is an important piece of this cosmic puzzle. The study of Cygnus X-1 also intersects with another fascinating field of research: the nature of spacetime itself. Black holes, by their very nature, challenge our understanding of the fabric of spacetime. At the event horizon, the boundary beyond which nothing can escape, spacetime is stretched to its limits. Time and space become so distorted that our traditional laws of physics no longer hold. The singularity at the center of the black hole, where the laws of physics break down completely, represents one of the greatest challenges in modern physics. It is here that general relativity, which governs the large-scale structure of the universe, must be reconciled with quantum mechanics, which governs the behavior of subatomic particles. This quest for a theory of quantum gravity is one of the holy grails of modern physics, and the study of black holes like Cygnus X-1 is key to making progress toward that goal. Cygnus X-1 is also important in the study of astrophysical phenomena such as accretion disks, relativistic jets, and X-ray emissions. The accretion disk of Cygnus X-1 is a particularly rich environment for studying the behavior of matter under extreme conditions. As material spirals inward toward the black hole, it is heated to millions of degrees, emitting copious amounts of X-rays. These X-rays are some of the brightest and most energetic emissions in the universe, and studying them can reveal a wealth of information about the properties of the black hole itself, as well as the physics of high-energy plasma. One of the most interesting aspects of Cygnus X-1 is its role in the study of relativistic jets. These jets are collimated streams of particles that are ejected from the vicinity of the black hole at nearly the speed of light. The exact mechanism by which these jets are produced is still not fully understood, but they are thought to be driven by the powerful magnetic fields that surround the black hole. These jets can stretch for thousands of light years and are visible across vast distances, making them one of the most striking features of black hole systems like Cygnus X-1. The study of these jets is crucial for understanding the role of black holes in the evolution of galaxies and the large-scale structure of the universe. Another fascinating aspect of Cygnus X-1 is its potential to reveal new physics beyond the standard model. The extreme conditions near the event horizon of the black hole make it an ideal testing ground for theories of quantum gravity, which attempt to reconcile general relativity with quantum mechanics. These theories propose that at extremely small scales, space-time is not continuous, but instead is made up of discrete, quantum, units. Understanding how matter behaves near the event horizon could offer insights into the fundamental nature of space-time and the quantum nature of gravity. Cygnus X-1 is one of the best places to test these theories, and future observations may lead to groundbreaking discoveries. Cygnus X-1 is not just one of the first black holes ever discovered, it is a treasure trove of scientific discovery. From its formation as a massive star to its evolution as a stellar mass black hole, Cygnus X-1 offers an unprecedented window into the mysteries of the universe. Its complex behavior, from accretion and X-ray emissions to relativistic jets and gravitational waves, makes it one of the most studied and most important systems in astrophysics. By studying Cygnus X-1, we are not only learning about black holes but also testing the fundamental laws of physics that govern the universe. As our observational technology continues to advance, we can only imagine the new insights that Cygnus X-1 and other black hole systems will provide in the years to come. Cygnus X-1 continues to offer a treasure trove of knowledge, and as technological advancements improve, so too will our understanding of these enigmatic celestial objects. As we've already seen, this stellar black hole system is crucial in many areas of astrophysics, from the evolution of galaxies to the study of extreme physics at the boundaries of spacetime. With future observations and the improvement of analytical techniques, scientists are hopeful that we will uncover even more secrets about Cygnus X-1 and similar systems. One of the fascinating aspects of Cygnus X-1's study is its role as an observable laboratory for high-energy astrophysics. As a compact object, a black hole like Cygnus X-1 provides one of the most extreme environments in the universe in which to study matter and energy. The disk of superheated material surrounding the black hole is a natural laboratory for studying plasma physics, the behavior of matter under extreme gravitational and magnetic fields, and the conversion of gravitational energy into radiation. It is at these extreme conditions that many of the most powerful and energetic phenomena in the universe are created. Black holes like Cygnus X-1 serve as windows into the processes that occur when the laws of physics are pushed to their limits. Cygnus X-1 is also an excellent example of how gravitational physics can provide valuable insights into fundamental science. The curvature of spacetime around a black hole is immense, and its influence stretches across vast distances. The study of this curvature can help scientists measure how light behaves near the event horizon, providing indirect evidence of the singularity at the center of the black hole. Such observations are incredibly challenging, as they require sophisticated instruments capable of detecting faint emissions, like the X-rays emitted by the accretion disk. But the data gathered by observatories like the Chandra X-ray Observatory and the European Space Agency's XMM Newton, along with the gravitational wave observatories, have already begun to yield critical information about these extreme environments. One of the key aspects of Cygnus X-1's legacy is its contribution to our understanding of the nature of time itself. Time, as we understand it in the framework of general relativity, is not a uniform, unchanging backdrop against which events occur. Instead, it can stretch and warp under the influence of massive objects like black holes. The intense gravitational field near Cygnus X-1 causes space-time to distort so dramatically that time itself is affected. This effect, known as gravitational time dilation, has been confirmed through observations of how the orbital periods of the star and the black hole vary over time. The further we delve into the study of these black holes, the more we realize how our understanding of time, space, and the universe itself is intertwined with these fascinating phenomena. One of the most interesting results of studying Cygnus X-1 is the glimpse it provides into the relationship between black holes and their host galaxies. While black holes like Cygnus X-1 are typically isolated in the cosmos, many black holes, particularly supermassive ones, lie at the centers of galaxies. These supermassive black holes are believed to play a critical role in the formation and evolution of galaxies. The study of Cygnus X-1 gives us a chance to understand the behavior of black holes in isolation, and how these isolated systems might compare to the behavior of black holes in galactic centers. We can draw important analogies between the way material is accreted onto Cygnus X-1 and how matter behaves around the supermassive black hole at the center of the Milky Way, Sagittarius A. Both systems serve as valuable analogues for understanding how black holes interact with their environments, and how they affect their host galaxies. One of the more profound implications of Cygnus X-1's study is its potential role in the broader context of the universe's evolution. Black holes like Cygnus X-1, particularly when they merge with other black holes or stellar remnants, may help seed the formation of supermassive black holes at the centers of galaxies. The mechanisms through which stellar mass black holes like Cygnus X-1 might grow and merge to form even larger black holes is an area of intense research. While we know that the growth of supermassive black holes is likely tied to the dynamics of galaxy formation, how stellar mass black holes contribute to this process remains a subject of active investigation. The mergers of black holes like those in the Cygnus X-1 system could potentially be a key step in this evolutionary chain. This brings us to the exciting field of gravitational wave astronomy. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made history by detecting the first gravitational waves emanating from the merger of two black holes. This detection confirmed a major prediction of Einstein's theory of general relativity and opened up a new era in astronomy. Cygnus X-1 is an ideal candidate for future gravitational wave observations. As the system evolves, it could one day undergo a black hole merger, generating gravitational waves that can be detected by instruments like LIGO and Virgo. The detection of gravitational waves from Cygnus X-1's merger would provide a wealth of information about the properties of black holes, as well as the physics of spacetime itself. It would also allow scientists to observe the final stages of a black hole's evolution and gain insights into how these mergers shape the universe at large. In addition to gravitational waves, Cygnus X-1 also provides valuable information about high-energy astrophysical phenomena such as gamma-ray bursts and relativistic jets. Gamma-ray bursts, GRBs, are some of the most powerful explosions in the universe, and although their exact origin is still debated, they are believed to be associated with the collapse of massive stars or the merger of compact objects like black holes and neutron stars. Cygnus X-1 is a potential source of such bursts, and understanding its behavior could help us pinpoint the physical processes behind these intense events. Additionally, the relativistic jets observed emanating from the black hole offer a glimpse into the physics of plasma acceleration and magnetohydrodynamics in extreme environments. These jets, which are thought to be powered by the black hole's magnetic field, provide another avenue of study for understanding how black holes interact with their environments. The study of Cygnus X-1, in many ways, represents a culmination of the modern quest to understand black holes and their role in the universe. From its groundbreaking discovery as one of the first black holes to its current status as an astrophysical laboratory, Cygnus X-1 continues to challenge our understanding of the universe and push the boundaries of science. The ongoing research and future discoveries related to this system will undoubtedly continue to reshape our understanding of gravity, space-time, and the nature of reality itself. As we continue to study Cygnus X-1, it's important to remember that this black hole is more than just a point in the sky. It's a symbol of the unknown. It's a place where the laws of physics break down, where time and space are distorted, and where the universe reveals some of its most profound mysteries. Just as the study of Cygnus X-1 has pushed the boundaries of human knowledge, so too will future discoveries about this enigmatic object and others like it. With each new piece of data, we draw closer to answering some of the most fundamental questions in physics. What happens at the event horizon? What is the true nature of the singularity at the heart of a black hole? How does matter behave in the presence of such extreme gravitational forces? And ultimately, what do black holes tell us about the fabric of the universe itself? Cygnus X-1 is a window into these mysteries. Its legacy is one of discovery, pushing the limits of what we know about the cosmos, and inspiring generations of scientists to continue exploring the most mysterious objects in the universe. In the end, black holes like Cygnus X-1 are not just astronomical curiosities. They are key to unlocking the deepest secrets of the universe. Cygnus X-1's status as one of the most studied black holes provides an essential starting point for tackling these fundamental questions. As we examine its inner workings, we encounter not only its extraordinary features but also the profound scientific principles that apply universally across black holes, irrespective of their size or location. By observing Cygnus X-1 in detail, scientists are slowly unraveling the puzzle of black hole physics, which has long remained an enigma. Every new discovery about Cygnus X-1 acts as a stepping stone toward resolving the cosmic mysteries that surround these celestial giants. The challenge in studying Cygnus X-1, and black holes in general, is that these objects do not emit light in the way stars or other cosmic entities do. Instead, black holes only reveal their presence through their influence on nearby matter. Whether through the bending of light via gravitational lensing or the production of powerful X-rays as material spirals into the event horizon, black holes like Cygnus X-1 are detected by their indirect effects on the environment around them. This indirect detection demands an innovative approach, making black holes one of the most difficult objects to study, but also one of the most fascinating. The study of Cygnus X-1 also gives us insights into the different forms of matter that surround black holes. The most intriguing of these is the accretion disk. This disk is composed of gas and dust drawn from the companion star. As this material spirals inward, it heats up to extremely high temperatures, emitting intense X-rays that can be detected by telescopes. The study of this disk allows scientists to infer the structure and dynamics of matter under extreme conditions, shedding light on how material behaves when it is caught in the intense gravitational grip of a black hole. Understanding the behavior of this hot, swirling disk of matter has implications not only for black hole physics but also for our broader understanding of plasma physics and accretion processes in other high-energy environments, such as quasars and active galactic nuclei. Further investigation into Cygnus X-1 has provided valuable insights into the role of magnetic fields in black hole systems. These magnetic fields can be incredibly strong in such environments, and they are thought to play a critical role in the formation of relativistic jets. These jets are one of the most striking features associated with many black holes, including Cygnus X-1. The jets themselves are composed of high-energy particles that are ejected at nearly the speed of light, and they extend for vast distances into space. The process by which the black hole generates these jets remains a subject of intense study. Current theories suggest that the magnetic field of the black hole, interacting with the spinning disk of material, is responsible for accelerating particles along the poles of the black hole, creating the jets. Understanding how these jets are formed and why they are so powerful could provide crucial insights into the behavior of high-energy plasma and the role of magnetic fields in astrophysical systems. The study of relativistic jets, particularly those emanating from Cygnus X-1, is an area where much progress has been made over the past several decades. These jets are some of the most energetic phenomena observed in the universe, and understanding how they form, accelerate, and interact with the surrounding environment is essential for grasping the broader context of astrophysical high-energy processes. Cygnus X-1 offers a relatively nearby and well-studied example of such a system, and as we improve our observational capabilities, such as through the use of high-resolution imaging and multi-wavelength observations, we are likely to uncover even more about how these jets behave and how they influence their host environments. Cygnus X-1's role in advancing our understanding of black holes is not limited to the study of matter surrounding these enigmatic objects. The system has also played a pivotal role in confirming the existence of black holes through its observed behavior. The discovery of Cygnus X-1 was groundbreaking because it provided the first solid observational evidence of a stellar mass black hole. At the time of its discovery, many scientists were skeptical about the existence of black holes, which had only been predicted theoretically. However, the behavior of Cygnus X-1, in particular, its X-ray emissions, provided irrefutable proof of the existence of black holes. This discovery was instrumental in transforming black holes from theoretical curiosities into real, observable objects, thus paving the way for decades of research into their properties and behavior. It is important to note that the identification of Cygnus X-1 as a black hole also helped to refine our understanding of the mass limits that govern the formation of stellar black holes. When the system was first studied, it became apparent that the object at the center of the system was too massive to be anything other than a black hole. This realization helped to confirm the concept of the upper mass limit for stellar black holes, which is crucial in understanding the end stages of a massive star's life cycle. Stars with masses greater than about 25 times that of our Sun will end their lives in a supernova explosion, leaving behind a black hole, but only if they are massive enough to undergo the necessary processes. Cygnus X-1 helped establish the threshold at which stars undergo this transition, providing insight into the life cycle of stars and their transformation into black holes. One of the ongoing debates surrounding Cygnus X-1 is the exact mass of the black hole at the system's center. The mass estimates for the black hole in Cygnus X-1 have varied somewhat over time as new techniques and more precise observations have been employed. Early estimates suggested a mass of about 10 solar masses, but more recent studies have refined this estimate. Today, the mass of the black hole is thought to be somewhere between 14 and 16 solar masses, making it a relatively large stellar mass black hole. This mass estimate places Cygnus X-1 in a class of black holes that straddles the line between stellar mass black holes and intermediate mass black holes, which have masses ranging from a few hundred to a few thousand solar masses. The precise mass of Cygnus X-1 remains an important area of research, as it will help to constrain models of black hole formation and evolution. Cygnus X-1 also provides critical data on the nature of the companion star, HD 226868. This massive blue supergiant star is in a highly elliptical orbit around the black hole, and its interactions with the black hole's gravity are crucial for understanding the system as a whole. The companion star is not only important for providing material to the accretion disk but also for serving as a probe of the black hole's mass and other characteristics. By studying the star's orbital motion and how it responds to the black hole's gravity, scientists are able to derive information about the black hole's mass, spin, and the structure of the surrounding space-time. The study of Cygnus X-1 has also led to important advancements in our understanding of the behavior of high-energy radiation, particularly X-rays and gamma rays. As the matter from the companion star is drawn toward the black hole, it is accelerated to extremely high velocities, heating up and emitting X-rays as it reaches the inner regions of the accretion disk. These X-rays are a key signature of black hole systems and are crucial for astronomers to detect and study these objects. Over the years, the detailed analysis of Cygnus X-1's X-ray emissions has provided invaluable data for understanding the physics of high-energy radiation, and the system has been extensively studied by space-based observatories such as the Chandra X-ray Observatory and the European Space Agency's XMM Newton satellite. Cygnus X-1 also plays an instrumental role in the ongoing quest to understand the general properties of accretion disks, and how they relate to the phenomena observed around black holes. The study of these disks provides a direct window into the environment surrounding a black hole, helping scientists uncover details about space-time distortions, the behavior of hot plasma under extreme conditions, and the fundamental physics of matter in the presence of intense gravitational fields. In the case of Cygnus X-1, observations of the accretion disk have revealed key information about how the disk structure changes in response to the black hole's gravitational influence, the rate at which material falls inward, and how the magnetic fields in the system contribute to the generation of powerful jets. This ongoing research is foundational for expanding our understanding of accretion phenomena in other types of astrophysical systems, including those in active galactic nuclei, where similar processes are at play on much larger scales. The role of magnetic fields around black holes is an area where Cygnus X-1 has provided profound insights. Magnetic fields play a crucial role in the dynamics of accretion disks, helping to explain how material is funneled toward the black hole and how high-energy particles are accelerated to relativistic speeds. Additionally, these magnetic fields are thought to be responsible for the formation of relativistic jets in systems like Cygnus X-1, which extend for vast distances into space. These jets can have significant effects on the surrounding interstellar medium, and understanding their formation process is vital for explaining the behavior of other black holes and compact objects across the universe. By observing the interaction between the black hole's magnetic field and the material in the accretion disk, scientists are gaining new insights into the mechanisms that govern the behavior of these powerful jets. Cygnus X-1 also serves as a natural laboratory for studying relativistic effects and the physics of spacetime near black holes. When material falls into the accretion disk, it is subject to intense gravitational forces, and these forces cause the material to behave in ways that are fundamentally different from how objects behave in less extreme environments. The intense gravity near the black hole causes time dilation effects, meaning that time passes more slowly near the event horizon compared to regions further away. This effect, predicted by Einstein's theory of general relativity, has been confirmed through detailed studies of black hole systems like Cygnus X-1. Observations of the system's X-ray emissions have allowed scientists to observe these relativistic effects in real time, providing a direct test of our understanding of gravity under extreme conditions. This ability to study the warping of spacetime and the behavior of matter under these conditions is one of the key reasons why black holes like Cygnus X-1 are so important to modern astrophysics. The study of black holes, and Cygnus X-1 in particular, is also a vital part of the broader quest to test the predictions of Einstein's theory of general relativity. While general relativity has been extensively tested in other contexts, such as the motion of planets and the bending of light around stars, black holes provide a unique opportunity to probe the theory's predictions in extreme environments. The immense gravitational fields around black holes create conditions where relativistic effects are most pronounced, and testing the theory in such an extreme setting allows scientists to push the boundaries of our understanding of gravity. The precise measurements of the orbital motions of Cygnus X-1's companion star, along with the detailed analysis of its X-ray emissions, have provided valuable data that helps scientists test the predictions of general relativity near the event horizon of a black hole. So far, these tests have confirmed that general relativity remains an accurate description of gravity, but future observations could provide clues about potential deviations or new physics that may arise in these extreme conditions. One particularly exciting area of research that has emerged from the study of Cygnus X-1 is the investigation into the spin of black holes. The spin of a black hole is a fundamental property that can affect the dynamics of the surrounding environment. Black holes can spin at different rates, and their spin can be described as a dimensionless parameter that ranges from 0, no spin, to 1, maximal spin. The spin of a black hole is thought to play a critical role in the formation of relativistic jets, the structure of the accretion disk, and even the way that matter falls into the black hole. By studying the behavior of Cygnus X-1's accretion disk and the motion of the companion star, scientists have been able to estimate the spin of the black hole at the system's center. This information is essential for understanding how angular momentum is transferred in black hole systems and for investigating the relationship between a black hole's spin and the production of high-energy radiation. Cygnus X-1 has also contributed significantly to our understanding of stellar evolution and the end stages of massive stars. The system consists of a massive star, HD 226868, that is in a close orbit around the black hole. This binary nature of Cygnus X-1 provides a unique opportunity to study the life cycle of stars and the processes that lead to the formation of black holes. The companion star is thought to be a massive blue supergiant, and its evolution over time has important implications for our understanding of how stars with high masses end their lives. These stars are too massive to end their lives as white dwarfs or neutron stars, and instead, they collapse into black holes when their nuclear fuel is exhausted. By studying the properties of the companion star and its interactions with the black hole, scientists are able to gain valuable insights into the processes that occur in the final stages of stellar evolution, providing a clearer picture of how black holes are formed and how they grow over time. The discovery of Cygnus X-1 also led to the identification of a new class of objects known as X-ray binaries. These systems, in which a stellar companion orbits a compact object like a black hole or neutron star, are a key area of research in modern astrophysics. X-ray binaries are important because they provide a direct means of studying compact objects and their interactions with surrounding matter. Cygnus X-1, as one of the first X-ray binaries to be identified, remains a cornerstone of this field, and it has provided invaluable data that has helped to refine our understanding of the formation and evolution of compact objects. The study of X-ray binaries also has broader implications for the study of stellar populations, as these systems represent a key link in the chain of stellar evolution and black hole formation. As technology advances, Cygnus X-1 continues to offer new insights and challenges to scientists. With the advent of next-generation telescopes, such as the James Webb Space Telescope and the upcoming LISA Gravitational Wave Observatory, astronomers are poised to gain even more detailed information about the black hole at the center of Cygnus X-1 and its companion star. These advancements will allow for the study of black holes with even greater precision, providing a deeper understanding of the fundamental processes that govern the behavior of matter under extreme conditions. With each new observation, Cygnus X-1 offers a glimpse into the mysteries of the universe, revealing secrets that have eluded humanity for centuries. Cygnus X-1 is not only a window into the extreme physics near a black hole but also plays a significant role in the broader context of astrophysical phenomena across the universe. The study of systems like Cygnus X-1 allows scientists to refine existing theories of gravity, matter, and energy under the most intense conditions, but it also helps establish new lines of research in the ongoing exploration of how stars live and die. Understanding the relationship between black holes and their stellar companions, such as those observed in Cygnus X-1, provides a crucial understanding of the mass distribution in the universe, the cycle of stellar life, and the mechanisms that lead to the formation of some of the most fascinating and mysterious objects in the cosmos. One of the most groundbreaking aspects of the Cygnus X-1 system is how it helped establish the concept of black holes as a real, observable phenomenon. Before Cygnus X-1's discovery, black holes were largely theoretical constructs, predicted by the equations of general relativity but never directly observed. The idea of an object with such immense gravity that not even light could escape seemed like science fiction to many. But the detection of X-rays emitted from the Cygnus X-1 system in the early 1970s changed that. The high-energy radiation that was being emitted from the region around the black hole, coupled with the mass of the compact object that could be inferred from the movement of the companion star, provided the first real evidence for the existence of a black hole. This discovery was a landmark achievement, and it established a new era of black hole research. The Cygnus X-1 system remains a crucial example for astronomers, offering a direct view of the interplay between the black hole and its companion star. It also helped lay the groundwork for subsequent discoveries of black holes in various types of stellar systems, including active galactic nuclei and even supermassive black holes at the centers of galaxies. These discoveries have revolutionized our understanding of the universe and continue to have profound implications for the study of cosmic evolution. In addition to being a crucial discovery for the study of black holes, Cygnus X-1 has had a profound impact on our understanding of the broader phenomena that occur in stellar systems. The system has provided invaluable data on the behavior of matter under extreme conditions, the effects of accretion disks and relativistic jets, and the ways in which magnetic fields interact with material in the vicinity of a black hole. These phenomena have broad implications for astrophysics, helping scientists study the evolution of galaxies, the creation of stellar populations, and the processes that govern the fate of stars and their remnants. Cygnus X-1's contribution to science extends beyond the discovery of black holes. The system has also provided important insights into the physics of X-ray binaries and other compact objects. The precise measurements of the companion star's motion and the behavior of the accretion disk have been instrumental in refining our models of compact object systems. This has led to a better understanding of the formation and evolution of X-ray binaries, and it has also opened up new avenues of research into the broader category of compact objects, including neutron stars and white dwarfs. The ongoing study of Cygnus X-1 has also provided a wealth of information on the spin of black holes. The spin of a black hole is one of its defining characteristics, and it plays a crucial role in determining the black hole's overall properties and its interaction with the surrounding environment. The study of Cygnus X-1 has allowed scientists to refine their models of black hole spin, helping to determine how this property influences the formation of relativistic jets, the structure of the accretion disk, and the distribution of material around the black hole. By combining observational data with theoretical models, astronomers have been able to estimate the spin of Cygnus X-1's black hole, gaining valuable insights into the behavior of black holes in the universe. The study of black holes like Cygnus X-1 also contributes to our understanding of the more exotic aspects of the universe, such as time dilation and the warping of spacetime. These phenomena, predicted by Einstein's theory of general relativity, are most pronounced near black holes, where gravity is at its most extreme. Observing the effects of these relativistic phenomena near Cygnus X-1 provides a unique opportunity to test the predictions of general relativity in a setting where they can be observed directly. The study of time dilation in such systems is particularly important, as it offers direct insights into how gravity affects the passage of time and how spacetime is warped by massive objects. Cygnus X-1 also contributes to the broader field of gravitational wave astronomy. Gravitational waves, ripples in spacetime caused by massive accelerating objects like merging black holes, were first predicted by Einstein and have only recently been detected. While Cygnus X-1 itself is not currently the source of gravitational waves, its study has provided valuable insights into the conditions and behaviors that lead to the formation of these ripples in spacetime. By improving our understanding of compact object systems and black hole dynamics, Cygnus X-1 helps pave the way for the detection of more black hole mergers, providing scientists with a clearer picture of the universe's most violent and energetic events. As technology continues to advance, scientists are able to observe Cygnus X-1 in new and more detailed ways. The use of advanced telescopes, including space-based observatories like the Chandra X-ray Observatory and the upcoming James Webb Space Telescope, allows astronomers to gather high-resolution data on the system's accretion disk, X-ray emissions, and the behavior of the companion star. These observations help refine our understanding of the physical processes occurring in the vicinity of the black hole and provide important clues about the structure of the universe on both large and small scales. The study of Cygnus X-1 also serves as a bridge between different branches of astrophysics. It connects the study of stellar evolution with the study of compact objects, the physics of black holes with the properties of X-ray radiation, and the behavior of matter under extreme conditions with the broader understanding of spacetime. This interdisciplinary approach is crucial for advancing our knowledge of the cosmos and for exploring the interconnected phenomena that shape the universe. Cygnus X-1's role in the study of black holes and compact objects continues to inspire new generations of scientists. The system has provided numerous discoveries, challenged existing models, and driven the development of new theories to explain the complex phenomena observed in these extreme environments. Its importance in the field of astrophysics cannot be overstated, as it remains one of the most studied and well-understood black holes in the universe. With each new observation and each new discovery, the mysteries of Cygnus X-1 continue to unfold, revealing the complex and fascinating nature of black holes and the forces that govern their behavior. As technology advances and our understanding of the universe deepens, Cygnus X-1 will continue to be a vital source of insight into the nature of space, time, and the fundamental forces that shape our universe. Cygnus X-1's place in astrophysical research is more than just as a singular object of fascination. It serves as a cornerstone of multiple scientific endeavors. With the ongoing advancements in observational technology and theoretical modeling, scientists are continually working to answer deeper questions about the black hole itself and the system as a whole. In many ways, Cygnus X-1 is like a cosmic laboratory where scientists can observe the fundamental laws of physics under extreme conditions. It's not just the black hole itself that's of interest, but the broader context in which it exists, offering new perspectives on phenomena like accretion, radiation, and relativistic jets. This object serves as a testing ground for the many ideas and theories that we have about the most extreme environments in the universe. The role of Cygnus X-1 in advancing our understanding of the interaction between a black hole and its companion star cannot be understated. One of the most fascinating aspects of this system is how the black hole's gravitational influence affects its companion, a massive blue supergiant star. The star's motion, as it orbits the black hole, is a key piece of the puzzle in determining the mass of the black hole itself. Through careful observation of the star's orbital dynamics, astronomers can calculate the black hole's mass with remarkable precision, and this provides a crucial insight into how black holes grow and evolve over time. Cygnus X-1 is also instrumental in advancing the study of X-ray binaries, which are systems consisting of a compact object, like a black hole or a neutron star, and a regular star that is supplying it with material. These systems are a common feature in the universe, and studying them allows scientists to better understand the life cycle of such systems, how matter behaves under extreme gravitational forces, and the mechanisms that lead to the emission of high-energy radiation. As one of the first X-ray binaries to be discovered, Cygnus X-1 remains one of the most studied systems in the field, offering a wealth of data that continues to be analyzed by astrophysicists worldwide. X-ray binaries like Cygnus X-1 are extremely valuable for a number of reasons. One of the most important is that they allow astronomers to observe the inner workings of black holes and neutron stars in a way that would not be possible with a black hole located in a more distant or isolated environment. The high-energy radiation emitted from the accretion disk and the intense gravitational fields present in the vicinity of the black hole allow scientists to study phenomena such as the behavior of matter as it spirals toward the event horizon, the formation of relativistic jets, and the way in which gravitational forces warp the fabric of space-time. Furthermore, the study of Cygnus X-1 has led to key developments in our understanding of high-energy astrophysics. Observations of the X-ray emission from the system have helped refine models of accretion disks, revealing how matter behaves as it is drawn into the black hole's gravitational grip. These accretion disks are fascinating structures, as they are not merely passive collections of gas, but rather active, dynamic regions that produce intense radiation. The X-rays emitted by Cygnus X-1 are primarily the result of the heating of this material as it spirals inward toward the black hole, a process that produces radiation across a broad spectrum of wavelengths, from visible light to X-rays and even gamma rays. The study of the system's relativistic jets also plays a crucial role in advancing astrophysical knowledge. These jets, which are often launched perpendicular to the accretion disk, are among the most energetic phenomena in the universe. Cygnus X-1 has been instrumental in providing astronomers with insights into how these jets are formed and how they interact with the surrounding environment. While much is still unknown about the exact mechanisms behind jet formation, observations of systems like Cygnus X-1 continue to provide key clues. For instance, the black hole's spin, the alignment of the accretion disk, and the interactions between the magnetic fields in the system all appear to play an important role in determining the direction and intensity of the jets. As scientists continue to study Cygnus X-1, they are also constantly revising and refining our models of black hole physics. Over the years, Cygnus X-1 has provided data that has challenged and extended our understanding of general relativity, the theory that governs our understanding of spacetime and gravity. The extreme conditions near the black hole, where gravity is so intense that even light cannot escape, create a natural laboratory for testing the predictions of general relativity. For instance, by observing how light behaves as it travels through the warp spacetime around the black hole, scientists can test the predictions of Einstein's theory under conditions that are otherwise impossible to replicate in a laboratory. Cygnus X-1 also plays an important role in the study of the potential existence of other exotic objects like primordial black holes, which are theorized to have formed in the early universe. While no definitive evidence of primordial black holes has been found, the study of more well-known black holes like Cygnus X-1 helps to refine our models of black hole formation and evolution. By understanding how typical stellar mass black holes form, scientists can apply this knowledge to theorize about the conditions that might lead to the creation of primordial black holes, potentially deepening our understanding of the earliest moments of the universe. In terms of technological advancements, Cygnus X-1 has been observed by an array of telescopes and observatories throughout its history. The advent of space-based telescopes such as the Chandra X-ray Observatory, the Hubble Space Telescope, and the recently launched James Webb Space Telescope has provided new insights into the system. These observatories allow for high-resolution imaging and spectroscopy in wavelengths such as X-rays, ultraviolet light, and infrared radiation, which are critical for studying the behavior of the material surrounding the black hole. By collecting data across multiple wavelengths, scientists can piece together a more complete picture of the physical processes occurring in Cygnus X-1 and other similar systems. The future of Cygnus X-1 research is even more promising, with the continued development of both observational and computational tools. Gravitational wave astronomy, for example, is an exciting new frontier in astrophysics. Gravitational waves, which were first directly detected in 2015 by the LIGO, Laser Interferometer Gravitational Wave Observatory, collaboration, provide a new way of observing the universe. While Cygnus X-1 itself is not currently the source of detectable gravitational waves, future observations may reveal gravitational wave signals from black hole mergers and other high-energy events that are related to systems like Cygnus X-1. The study of such gravitational waves could help further refine our understanding of black hole mergers, the dynamics of compact binary systems, and the structure of spacetime itself. One of the most exciting aspects of Cygnus X-1 is how it exemplifies the interconnected nature of modern astrophysical research. The study of this black hole and its companion star touches upon numerous different fields of science, from stellar evolution to high-energy radiation, to the fundamental laws of physics that govern the universe. As our knowledge of black holes and their environments continues to grow, the insights gained from Cygnus X-1 will continue to be pivotal in shaping our understanding of some of the most enigmatic and powerful phenomena in the cosmos. Ultimately, Cygnus X-1 remains one of the most important and fascinating objects in the universe. Its discovery and subsequent study have not only confirmed the existence of black holes but have also pushed the boundaries of human knowledge about the extreme and mysterious nature of our universe. As new discoveries continue to be made and new technologies come online, the role of Cygnus X-1 in astrophysics will only grow, providing deeper insights into the nature of black holes, stellar evolution, and the fundamental forces that govern our reality. The ongoing study of Cygnus X-1 extends well beyond the immediate boundaries of its own system, having profound implications for our broader understanding of astrophysics and cosmology. With each new generation of telescopes and each advancement in observational techniques, we are able to peer deeper into the heart of this black hole and learn more about its complex behavior. The system remains an ideal candidate for testing and refining our models of the universe, offering a close-up view of phenomena that were once relegated to the realm of theory and speculation. In particular, Cygnus X-1 has been instrumental in providing key insights into the behavior of accretion disks, which are ubiquitous around black holes, neutron stars, and other compact objects. The material that is drawn into these disks spirals inward under the influence of the black hole's intense gravitational field, heating up to extreme temperatures as it gets closer to the event horizon. This process leads to the emission of high-energy radiation, which can be detected across a range of wavelengths, from X-rays to gamma rays. The study of accretion disks around black holes like Cygnus X-1 has enabled astronomers to understand the structure, dynamics, and radiative properties of these enigmatic objects in unprecedented detail. What makes Cygnus X-1 so valuable is not just its status as one of the first black holes to be discovered, but also the fact that it is part of a relatively close binary system, which allows astronomers to study it in detail. The system consists of a stellar mass black hole and a massive blue supergiant star, a configuration that makes it a perfect candidate for testing theories about how black holes grow, how they interact with their companion stars, and how they produce the powerful jets and radiation that are observed in many black hole systems. Over the years, Cygnus X-1 has become a key source of data for scientists studying black hole formation and evolution. One of the most intriguing aspects of this system is the fact that the black hole is not alone. It's part of a binary system, in which the companion star is supplying material to the black hole. This interaction provides astronomers with a wealth of information about the behavior of matter in extreme gravitational fields. The way in which the gas from the companion star is funneled into the black hole's accretion disk, and the way that this material is ultimately heated to produce X-rays, is a central feature of Cygnus X-1's high-energy behavior. Through these observations, scientists have been able to refine their models of accretion, which is one of the most fundamental processes in astrophysics. The study of accretion disks is key to understanding how black holes grow and evolve over time, and how they influence their surroundings. The dynamics of the material in the accretion disk are complex, and the way in which the material spirals inward under the influence of gravity leads to the formation of powerful jets and intense radiation. By studying systems like Cygnus X-1, astronomers can better understand these processes and improve their understanding of how black holes interact with their environment. In addition to providing insights into accretion, Cygnus X-1 has also been crucial for advancing our understanding of relativistic jets. These high-speed outflows of gas, often seen in systems like Cygnus X-1, are one of the most striking features of black hole systems. The jets, which are typically launched perpendicular to the accretion disk, are powered by the rotation of the black hole and the intense magnetic fields in the system. Observing how these jets form, how they interact with the surrounding environment, and how they are aligned with the black hole's spin, has provided astronomers with valuable information about the physics of black holes and the nature of the extreme environments that surround them. The fact that Cygnus X-1 is such a well-studied system has allowed astronomers to test many different theories about black holes and their behavior. The system is ideal for testing Einstein's general theory of relativity, as the extreme gravitational forces near the black hole make it a natural laboratory for studying space-time curvature. Through precise measurements of the motion of the companion star and the X-ray emission from the accretion disk, scientists have been able to test predictions of general relativity under some of the most extreme conditions possible. These tests have helped to confirm the validity of Einstein's theory in the vicinity of a black hole, but they have also led to new questions about how gravity operates at the smallest scales. In addition to its role in testing general relativity, Cygnus X-1 has also contributed to our understanding of black hole formation and evolution. Black holes like Cygnus X-1 are thought to form from the collapse of massive stars, and studying the mass and properties of the black hole in this system can provide important clues about the process of stellar collapse. Through careful observations of the companion star's orbit, astronomers have been able to estimate the mass of the black hole and learn about the conditions under which it formed. This information is crucial for understanding the broader population of black holes in the universe, including those that are formed through different mechanisms, such as mergers between compact objects. The study of Cygnus X-1 has also provided valuable information about the history of black hole accretion and the role that black holes play in the evolution of galaxies. As black holes grow by accreting material from their surroundings, they can release enormous amounts of energy, which can have a profound impact on their environment. In some cases, this energy can drive powerful outflows and jets that influence the formation of stars and the evolution of galaxies. By studying Cygnus X-1, scientists can gain insights into how black holes interact with their environments and how they contribute to the larger-scale structure of the universe. Cygnus X-1 has become an iconic object in the field of astrophysics, not only for its role in confirming the existence of black holes, but also for the wealth of information it continues to provide about the most extreme objects in the universe. As new technologies and methods of observation come online, it is likely that we will continue to learn more about this remarkable system. The discovery of gravitational waves, for instance, offers a new way of studying black holes and their mergers, and future gravitational wave detections from systems like Cygnus X-1 could provide new insights into the behavior of compact objects. In many ways, Cygnus X-1 is the prototype of a class of objects that are central to our understanding of the universe. As one of the first black holes discovered, it set the stage for subsequent discoveries in high-energy astrophysics, and it continues to be an important source of data and inspiration for scientists working to unlock the mysteries of the universe. Its role in the study of accretion, relativistic jets, and the behavior of matter in extreme gravitational fields makes it an essential object of study in the quest to understand the fundamental forces that govern the cosmos. As we continue to refine our understanding of black holes and the environments around them, Cygnus X-1 will undoubtedly remain one of the most important objects in our quest to comprehend the fundamental nature of the universe. Whether through direct observations of its X-ray emissions, its accretion disk, or the relativistic jets that emanate from its poles, the study of Cygnus X-1 promises to yield new insights into the nature of space-time, gravity, and the forces that shape our universe. Through its continued study, we will undoubtedly push the boundaries of our knowledge, uncovering deeper truths about the workings of the cosmos that have remained hidden for centuries. As we continue to explore the complexities of Cygnus X-1, it is important to consider how this system has also played a role in expanding our broader understanding of the universe. While it is easy to view Cygnus X-1 as a singular object of study, it represents just one piece of a much larger cosmic puzzle. The insights gleaned from its study extend far beyond the confines of this single system, offering profound implications for everything from star formation to the behavior of matter under extreme gravitational forces. One of the most significant contributions of Cygnus X-1 to modern astrophysics has been its influence on the theory of stellar evolution. The massive star that accompanies the black hole, once a companion in the early stages of the system's life, provides us with a clear example of how stars evolve, particularly in binary systems. In many ways, the study of this system can serve as a proxy for the complex and often violent processes that lead to the formation of compact objects, such as black holes and neutron stars, throughout the universe. These processes are not unique to Cygnus X-1, and by studying it, scientists can make inferences about other systems with similar characteristics, expanding our understanding of the life cycle of stars in the universe. The evolution of the companion star in Cygnus X-1 itself is an essential part of this story. Massive stars, like the one in this system, evolve rapidly, consuming their nuclear fuel and going through violent phases that end with their eventual collapse into black holes. The presence of the black hole in Cygnus X-1 offers an ideal environment for studying this final phase of a star's life, as the gravitational pull of the black hole distorts the space-time around it, allowing scientists to closely observe how material is transferred from the dying star to the black hole. The resulting interactions provide an invaluable opportunity to examine the processes that take place at the end of a star's life cycle. Moreover, the fact that Cygnus X-1 exists as a binary system with a stellar companion allows scientists to use it as a natural laboratory for studying the dynamics of binary systems. The gravitational interactions between the black hole and its companion star result in a complex exchange of energy and mass, providing astronomers with the tools needed to refine their models of how such systems evolve. For example, the orbit of the companion star is influenced by the gravitational pull of the black hole, which in turn affects the amount of material the black hole can draw in from the star. Studying these interactions offers insight into the interplay between black holes and their environment, as well as the broader mechanisms that govern the behavior of compact objects in the universe. Understanding the behavior of stars in binary systems is also essential for predicting the fate of similar systems in the universe. As astronomers discover more black holes and neutron stars in binary systems, the lessons learned from Cygnus X-1 will be crucial for predicting the future evolution of these objects. The study of binary systems also allows scientists to better understand the types of supernovae that occur when massive stars reach the end of their lives, as well as the processes that lead to the formation of black holes and neutron stars. In many ways, Cygnus X-1 has opened the door to understanding the variety of ways in which black holes can form, evolve, and interact with their surroundings. Additionally, the study of Cygnus X-1 and other black hole systems has provided crucial insights into the broader population of black holes throughout the universe. Cygnus X-1, as one of the first black holes ever discovered, serves as a key reference point for understanding the behavior of black holes of stellar mass. Its size, mass, and accretion properties provide a benchmark for comparing other black holes that are discovered in a variety of environments, from binary star systems to the centers of galaxies. This comparative approach is central to developing a more nuanced understanding of black hole physics, as it allows scientists to explore the different factors that influence black hole formation and growth. The implications of studying black holes like Cygnus X-1 extend well beyond the realm of astrophysics. In recent years, there has been increasing interest in the potential role of black holes in cosmology. Cygnus X-1, like many other black hole systems, is thought to be a crucial player in the larger processes of galaxy formation and evolution. Through their interactions with their environment, black holes can have a significant impact on the structure of the galaxies they reside in, influencing everything from star formation to the dynamics of galactic nuclei. In this sense, the study of black holes is intrinsically tied to our understanding of the cosmos on the largest scales. One area where black holes like Cygnus X-1 may play a pivotal role is in the understanding of the so-called feedback processes in galaxies. Feedback refers to the idea that the energy released by a black hole, through mechanisms like radiation, winds, and jets, can have a profound effect on the gas and stars that surround it. In particular, the release of energy from a supermassive black hole in a galaxy's center can regulate the growth of the galaxy itself, preventing overaccumulation of gas and stars. Similarly, the study of stellar mass black holes like Cygnus X-1 can offer clues about how these feedback mechanisms operate on a smaller scale, helping to reveal how black holes contribute to the overall growth and evolution of galaxies. Moreover, black holes may also have important implications for our understanding of the large-scale structure of the universe. Some theories suggest that black holes could play a role in the formation of cosmic structures such as galaxy clusters. By studying the growth and behavior of black holes in various environments, scientists may be able to gain new insights into the processes that govern the formation of the universe on the largest scales. Cygnus X-1, as one of the most studied black holes in the universe, is well positioned to contribute to this field of research, offering a closer look at the role of black holes in shaping the structure of the cosmos. In the context of Cygnus X-1, one of the most fascinating aspects is the possibility that it might be part of an even larger network of black holes and compact objects in our galaxy. Over the years, astronomers have discovered a number of other X-ray binaries, systems in which a black hole or neutron star is in a binary relationship with a companion star, that share many similarities with Cygnus X-1. By studying these systems in tandem, scientists are able to piece together a more complete picture of how black holes interact with their environments, and how they influence the evolution of the galaxies they inhabit. Furthermore, as technological advancements continue to improve our observational capabilities, we are likely to learn even more about Cygnus X-1 and similar black hole systems. New observatories, such as the Event Horizon Telescope, EHT, which famously captured the first-ever image of a black hole's event horizon in the M87 galaxy, are pushing the boundaries of what we can observe in the universe. These advances, along with the continued development of gravitational wave observatories, are expected to lead to new discoveries about the physics of black holes, and could reveal new information about the formation and growth of stellar mass black holes like Cygnus X-1. The implications of these discoveries for our understanding of the universe are profound. As we probe deeper into the nature of black holes, we not only gain insight into the most extreme environments in the universe but also unlock new clues about the fundamental workings of space-time and the forces that shape the cosmos. The study of Cygnus X-1, as one of the most important black holes in our cosmic backyard, will continue to play a central role in these endeavors, guiding us toward a deeper understanding of the universe's most enigmatic objects. As our knowledge of black holes continues to expand, the contributions of Cygnus X-1 will remain a cornerstone in our quest to understand the universe's most mysterious and powerful phenomena. From its role in confirming the existence of black holes to its ongoing contributions to the study of accretion, relativistic jets, and the behavior of matter under extreme conditions, Cygnus X-1 is not just an object of scientific curiosity. It is a symbol of the infinite possibilities that await us as we continue to explore the cosmos. Cygnus X-1, being one of the most studied black holes in the universe, continues to inspire scientific exploration and capture the imagination of both astronomers and the general public. Its unique characteristics not only challenge our understanding of fundamental physics but also provide an unparalleled opportunity to investigate the extremes of space-time, gravitational forces, and the behavior of matter in the vicinity of a black hole. The more we learn about this remarkable object, the closer we get to unraveling some of the most profound mysteries of the universe. At the heart of Cygnus X-1 is the immense gravitational pull of the black hole itself, which dictates the behavior of everything around it, including its companion star. The dynamics of this system offer a laboratory for testing the predictions of general relativity, which describes how spacetime is warped by massive objects like black holes. The fact that Cygnus X-1 is relatively close to Earth, in astronomical terms, gives us a unique opportunity to study the effects of extreme gravitational forces in a way that would be impossible with more distant black holes. One of the key features of Cygnus X-1 is the accretion disk that forms around the black hole. This disk is made up of gas and other matter that is gradually pulled toward the black hole by its intense gravitational field. As the material spirals inward, it is heated to millions of degrees, emitting vast amounts of X-rays and other forms of radiation. This radiation is a telltale sign of the black hole's presence and has been crucial for identifying Cygnus X-1 as a black hole system. The study of accretion disks around black holes is essential for understanding how matter behaves in the extreme conditions near a black hole, and it also has broader implications for astrophysics, such as providing insights into the formation and growth of supermassive black holes at the centers of galaxies. The presence of a relativistic jet in Cygnus X-1 adds another layer of intrigue to the system. These jets, which are launched from the poles of the black hole, are composed of highly energetic particles moving at nearly the speed of light. They extend vast distances into space, often stretching well beyond the host star. The exact mechanisms behind the formation of these jets are still not fully understood, but their study is crucial for understanding how black holes interact with their surroundings and how they can influence the broader galactic environment. The fact that Cygnus X-1 is a source of these relativistic jets offers a unique opportunity to study this phenomenon up close and provides important clues about the processes that govern the behavior of black holes and their accretion disks. One of the most fascinating aspects of Cygnus X-1, and black holes in general, is the fact that they challenge our understanding of the nature of spacetime itself. According to Einstein's theory of general relativity, the gravitational field near a black hole is so intense that it warps the fabric of spacetime, creating a singularity at the center of the black hole where the laws of physics, as we know them, break down. At this point, matter is crushed to an infinite density, and time and space behave in ways that defy our conventional understanding. The study of black holes like Cygnus X-1 is, in many ways, a quest to understand the very nature of the universe and the limits of human knowledge. What happens at the event horizon, the boundary beyond which not even light can escape? What occurs inside the event horizon, where nothing can be observed directly? These are some of the fundamental questions that physicists hope to answer through the study of black holes like Cygnus X-1. In addition to offering insights into the nature of spacetime and the extreme physics of black holes, Cygnus X-1 also plays an important role in our understanding of the broader universe. The discovery of black holes, particularly those in binary systems like Cygnus X-1, has provided a valuable tool for exploring the evolution of stars and galaxies. By studying the behavior of the companion star in this system, astronomers can learn more about how massive stars evolve, go through their life cycles, and eventually collapse into black holes. In fact, the discovery of Cygnus X-1 has been instrumental in expanding our understanding of the end stages of massive stars, providing clues about how black holes form and how they interact with their surroundings. Furthermore, the study of Cygnus X-1 has implications for our understanding of the broader distribution of black holes in the universe. As astronomers discover more and more black holes, both in binary systems and in isolation, they are able to build a more complete picture of the different types of black holes that exist. Stellar mass black holes, like Cygnus X-1, are thought to form from the remnants of massive stars, while supermassive black holes, which reside at the centers of most galaxies, are much larger and likely formed through entirely different processes. Understanding the differences between these two types of black holes, and the mechanisms that lead to their formation, is a central goal in modern astrophysics, and Cygnus X-1 serves as an important piece of this puzzle. As technology continues to improve, our ability to observe and study black holes like Cygnus X-1 will only continue to grow. The development of more powerful telescopes, such as the James Webb Space Telescope, promises to provide new insights into the properties of black holes and their environments. The ability to observe the radiation emitted by Cygnus X-1 and other black holes with unprecedented precision will allow scientists to probe deeper into the mysteries of these objects and refine our models of their behavior. In addition, the continued advancement of gravitational wave detectors, such as LIGO, will open up new avenues for studying the interactions of black holes and binary systems, providing a new way to observe the mergers of black holes and other compact objects. The discovery of Cygnus X-1 and its ongoing study represents a major milestone in our understanding of black holes, stellar evolution, and the extreme physics that govern the universe. But it is also just one step along the way in a much larger journey of exploration. Every new observation, every new discovery, adds to our understanding of the universe's most mysterious objects and brings us closer to answering some of the most profound questions in astrophysics. As we continue to probe the depths of space and study systems like Cygnus X-1, we are reminded of the vastness of the cosmos and the incredible complexity that lies beyond our planet. The significance of Cygnus X-1 in the broader context of astronomy cannot be overstated. It has not only contributed to our understanding of black holes but has also led to new discoveries about the life cycles of stars, the formation of compact objects, and the nature of space-time. Its role in the history of black hole research is foundational, and its continued study promises to yield new insights into the behavior of matter and energy in the most extreme conditions known to science. The legacy of Cygnus X-1 will undoubtedly continue to shape the future of astrophysics for generations to come, and its influence will extend far beyond the confines of this one object, impacting our understanding of the entire universe. As we look to the future, it is clear that Cygnus X-1 will remain at the forefront of black hole research, continuing to inspire scientific inquiry and offering new opportunities for discovery. Whether it is through the study of its accretion disk, the investigation of its relativistic jets, or the exploration of the fundamental properties of black holes themselves, this system will continue to play a pivotal role in our quest to understand the universe's most enigmatic and powerful objects. The journey of exploration that Cygnus X-1 represents is far from over, and the future of black hole research is brighter than ever. Cygnus X-1's prominence in the scientific community is not just a result of its dramatic physical properties, or its status as one of the first confirmed black holes. Its discovery marked a turning point in our understanding of the cosmos. Prior to the 1960s, black holes were merely theoretical objects within the realm of general relativity. Though the concept had been introduced by Carl Schwarzschild in the early 20th century, the idea of a celestial object that could trap light, or more fundamentally alter the fabric of space-time, seemed far-fetched. Cygnus X-1, however, provided the first solid evidence that such objects could exist. This breakthrough sparked a revolution in astrophysics, forever changing the way we think about stars, gravity, and the universe itself. The initial discovery of Cygnus X-1 in 1964 was not by accident. A team of scientists aboard a sounding rocket detected high-energy X-rays coming from a region in the Cygnus constellation. The X-ray source was unusual in that it emitted radiation far more intense than what could be explained by any known stellar phenomena at the time. Scientists had no clear idea of what this object was, but its X-ray signature made it an intriguing target for further investigation. Over the years, This enigmatic source, now known as Cygnus X-1, would reveal its identity as a stellar mass black hole. The process by which Cygnus X-1 was identified as a black hole began with the recognition that the object was part of a binary system. In the early 1970s, astronomers were able to determine that Cygnus X-1 was paired with a massive blue supergiant star named HD 226868. Observations showed that the star was orbiting an unseen companion with a mass much greater than that of a neutron star. This unseen companion was later identified as a black hole, its mass estimated to be about 14 to 15 times that of the Sun, putting it firmly in the category of stellar mass black holes. The detection of these X-rays coming from the accretion disk surrounding the black hole confirmed its presence, making Cygnus X-1 one of the first objects to be definitively classified as a black hole. The primary mechanism by which Cygnus X-1 generates such powerful X-ray radiation lies in the process of accretion. As matter from the companion star is pulled toward the black hole, it forms a swirling disk around the black hole's event horizon. The material in the disk is compressed and heated to extreme temperatures as it spirals inward, generating high-energy radiation in the form of X-rays. This process is not only a fascinating demonstration of the effects of gravity, but also provides a unique window into the behavior of matter under the most extreme conditions. The study of the accretion disk around Cygnus X-1 is particularly valuable because it serves as a natural laboratory for understanding the physics of black holes. The material in the disk is subject to gravitational forces so strong that it experiences intense heating and friction, causing it to glow brightly in the X-ray spectrum. These emissions give us clues about the structure and composition of the disk itself, as well as the behavior of matter in the intense gravitational field near a black hole. Researchers have also been able to study the inner workings of the black hole's event horizon, where the escape velocity exceeds the speed of light, and to investigate the limits of general relativity. Another compelling aspect of Cygnus X-1 is the relativistic jets that emerge from the poles of the black hole. These jets are composed of highly energized particles that are propelled away from the black hole at nearly the speed of light. The existence of these jets provides valuable insight into the ways in which black holes can interact with their surroundings, exerting forces on matter far beyond their immediate vicinity. While the exact mechanisms that give rise to these jets are still the subject of active research, it is believed that they are driven by the accretion process and the intense magnetic fields generated by the rotating black hole. The study of the jets produced by Cygnus X-1 has also opened up new possibilities for understanding the role of black holes in the broader structure of galaxies. In particular, astronomers have observed that the relativistic jets emitted by black holes in active galactic nuclei, AGNs, can have profound effects on the surrounding galaxy. These jets can trigger star formation, regulate the growth of the supermassive black hole at the center of the galaxy, and even influence the formation of galactic clusters. The study of Cygnus X-1 and other stellar mass black holes offers important clues about how these processes work on both small and large scales, shedding light on the evolution of galaxies and the role of black holes in shaping the universe. In addition to its scientific significance, Cygnus X-1 has captured the imagination of the public and has become a symbol of the unknown and the mysterious. The idea of an object that warps space-time and consumes everything in its vicinity, including light, is a concept that has fascinated people for generations. The black hole's reputation has been bolstered by its frequent appearance in popular media, from science fiction films to documentaries and books. Its connection to the Cygnus constellation, with its evocative name, adds an additional layer of intrigue, inviting people to look up at the night sky and wonder about the secrets hidden in the vastness of space. Despite the advancements made in our understanding of Cygnus X-1, there is still much we don't know about it. For example, although we can observe the X-rays emitted by the accretion disk and other radiation from the system, the details of what happens inside the event horizon remain elusive. According to the laws of general relativity, nothing, not even light, can escape the black hole's gravitational grip once it crosses the event horizon. This creates a fundamental challenge for scientists, as no direct observations of the black hole's interior are possible. Instead, astronomers rely on indirect evidence to study the black hole and its environment. As technology improves, new instruments are being developed to study Cygnus X-1 and other black holes with greater precision. One of the most exciting developments in this regard is the Event Horizon Telescope, EHT, which aims to capture images of black holes by observing the radiation emitted by the gas around their event horizons. In 2019, the EHT collaboration made history by producing the first-ever image of a black hole, located at the center of the galaxy M87. This breakthrough was a significant step forward in our understanding of black holes and provides a new way to study their properties. It is only a matter of time before the EHT or similar instruments provide new insights into the nature of Cygnus X-1 and other stellar mass black holes. The study of Cygnus X-1 has also contributed to the development of new theoretical models in astrophysics. For example, the precise measurements of the mass and spin of the black hole have helped refine our understanding of how black holes form and evolve. It is thought that black holes like Cygnus X-1 are born when massive stars exhaust their nuclear fuel and undergo a supernova explosion. The core of the star then collapses under the force of gravity, forming a black hole. Understanding the conditions under which these stellar mass black holes form and the subsequent evolution of their properties is a central question in modern astrophysics. Cygnus X-1 has also played a significant role in our understanding of the broader population of black holes in the universe. By studying this particular system, astronomers have gained insights into the distribution of black holes in the Milky Way and other galaxies, as well as the processes that govern their formation and growth. This research has helped to identify other stellar mass black holes, as well as supermassive black holes at the centers of galaxies, further expanding our understanding of the different types of black holes that exist. In many ways, Cygnus X-1 is a microcosm of the universe itself, a place where the fundamental forces of nature are at their most extreme. The interactions between the black hole and its companion star, the behavior of matter in the accretion disk, and the powerful relativistic jets all provide a glimpse into the workings of the universe on the grandest scale. As scientists continue to explore the mysteries of black holes, systems like Cygnus X-1 will remain at the forefront of research, providing valuable clues about the nature of gravity, space-time, and the fundamental laws of physics. The ongoing study of Cygnus X-1 is not just an exploration of a distant object, but a journey into the heart of the cosmos. With each new discovery, we are drawn deeper into the unknown, encountering new questions that challenge our understanding of the universe. The story of Cygnus X-1 is far from over, and its role in the future of black hole research is assured. For as long as humans look to the stars, Cygnus X-1 will remain one of the most compelling and mysterious objects in the universe, continuing to captivate the imagination and push the boundaries of human knowledge. As we continue to explore the mysteries of Cygnus X-1, it becomes increasingly evident that its existence plays a crucial role in the broader understanding of stellar evolution and the dynamics of the universe. The insights gained from studying this system have far-reaching implications, not just for black holes, but for the very nature of matter, energy, and the fundamental laws that govern everything in the cosmos. The complexities of the black hole's interaction with its companion star and the various forces at play within the system provide us with a rare opportunity to observe the interplay of astrophysical phenomena on a level that few other objects can offer. One of the key areas of interest for researchers studying Cygnus X-1 is the phenomenon of gravitational wave emission. Gravitational waves are ripples in the fabric of spacetime that propagate outward from violent cosmic events, such as the collision or merger of black holes or neutron stars. In recent years, the detection of gravitational waves by the Laser Interferometer Gravitational Wave Observatory, LIGO, has provided scientists with a new way to observe the universe. Although the waves generated by Cygnus X-1 have not been directly detected, the ongoing study of this system offers a valuable reference point for understanding the behavior of black holes and binary systems. The behavior of Cygnus X-1's accretion disk and the interactions between the black hole and its companion star are also crucial for understanding the evolution of stellar mass black holes. In some cases, the accretion disk can undergo periodic outbursts, which are thought to be caused by the black hole's gravitational pull on the material in the disk. These outbursts can have a significant impact on the surrounding environment, and studying these processes can provide valuable insights into the mechanisms of mass transfer and binary systems. By comparing the observations of Cygnus X-1 with other X-ray binaries, scientists are able to build a more comprehensive picture of the various types of stellar mass black holes and the processes that govern their evolution. As technology continues to advance, our ability to observe and analyze Cygnus X-1 in greater detail increases. The development of next-generation space telescopes, such as the James Webb Space Telescope, JWST, and the planned Athena mission, will provide astronomers with unprecedented views of black holes and their surroundings. These telescopes will be able to detect the faint X-ray emissions from the accretion disks of black holes, as well as the radiation from relativistic jets, allowing for more detailed studies of the material that surrounds these objects. Such observations will be instrumental in answering some of the most fundamental questions about the nature of black holes, their formation, and their role in the evolution of galaxies. The study of Cygnus X-1 is also closely linked to the broader quest for understanding the mysteries of dark matter. While Cygnus X-1 itself is not a source of dark matter, the research surrounding black holes and their interaction with normal matter can provide valuable clues about the nature of dark matter and how it behaves in the presence of gravity. By studying the properties of the black hole's accretion disk, scientists can learn more about the distribution of matter in the surrounding region and how it is influenced by gravitational forces. This, in turn, may help to shed light on the elusive properties of dark matter, which remains one of the most profound unsolved mysteries in modern physics. Cygnus X-1 also holds particular interest for those studying the nature of time and space. The concept of time dilation, a key feature of Einstein's theory of general relativity, plays a significant role in the behavior of objects near black holes. The immense gravitational pull of Cygnus X-1 warps spacetime in such a way that time behaves differently near the black hole than it does far away from it. For example, an observer approaching the event horizon of the black hole would perceive time to slow down, while an external observer would see time speeding up. This warping of time is not just a theoretical concept but a real phenomenon that has been confirmed through the study of various astronomical systems. By observing Cygnus X-1, scientists can gain a deeper understanding of how time behaves under extreme conditions, furthering our comprehension of the fabric of the universe itself. Moreover, Cygnus X-1's relatively close proximity to Earth compared to other black holes makes it an ideal target for studying the extreme physics of black holes. While other black holes in distant galaxies are difficult to observe in detail, the proximity of Cygnus X-1 allows astronomers to obtain high-resolution data on its behavior, including the movement of the companion star, the properties of the accretion disk, and the nature of the relativistic jets. This has made Cygnus X-1 a benchmark for testing and refining our models of black hole physics. As new observational techniques are developed, we will undoubtedly gain a more nuanced understanding of how these enigmatic objects interact with their surroundings and how they affect the evolution of galaxies over time. Cygnus X-1's place in scientific history is firmly secured, but its continued study ensures that it will remain at the forefront of black hole research for years to come. The insights gained from this particular system will continue to influence our understanding of black holes and the broader universe. As technology progresses and our ability to observe the cosmos improves, Cygnus X-1 will remain a key object of study, offering new opportunities to unlock the secrets of the universe and the forces that shape it. Looking toward the future, the ongoing exploration of Cygnus X-1 will undoubtedly lead to further breakthroughs in the fields of astrophysics and cosmology. New instruments and observational techniques, coupled with advances in theoretical models, will allow us to probe even deeper into the mysteries of this extraordinary system. From the study of the black hole's mass and spin to the detection of gravitational waves and the exploration of relativistic jets, Cygnus X-1 will remain a vital piece of the cosmic puzzle, providing us with a window into the heart of the universe. Cygnus X-1 is more than just an astronomical object. It is a symbol of humanity's unyielding curiosity and our quest to understand the most fundamental aspects of the universe. It represents the unknown, the mysterious, and the ever-present drive to push the boundaries of knowledge. As we continue to study this enigmatic black hole, we are reminded that the universe is far more complex and beautiful than we can even imagine, and that there is still so much more to discover in the vastness of space. The study of Cygnus X-1 has enriched our understanding of the universe, deepened our appreciation for the complexities of black holes, and provided a glimpse into the most extreme environments imaginable. It has inspired generations of scientists and researchers to continue pushing the limits of what we know, and it will undoubtedly continue to inspire future generations to look to the stars with wonder and curiosity. Cygnus X-1's story is far from over, and as our understanding of the cosmos evolves, so too will our understanding of this extraordinary and elusive black hole. Cygnus X-1 remains one of the most captivating astronomical objects in the cosmos, continuing to yield new discoveries and challenges for the field of astrophysics. As our understanding of black holes expands, it becomes increasingly clear that Cygnus X-1 is more than just a fascinating outlier in the universe. It is a cornerstone for testing the fundamental theories that shape our understanding of spacetime, gravity, and the interactions between matter and energy. Its continued study provides critical insights into the nature of black holes, and its mysteries are far from being fully unraveled. Over the decades, as scientists have refined their methods of observation and developed more sophisticated tools, our ability to probe the properties of Cygnus X-1 has improved dramatically. The discovery of the black hole's mass and the eventual understanding of its connection to a massive companion star were pivotal moments in the history of astronomy. But what makes Cygnus X-1 particularly intriguing is its continued role as a natural laboratory, where astrophysicists can explore the extreme conditions that arise around a black hole. As the next generations of telescopes and detectors come online, Cygnus X-1 will undoubtedly remain an essential target for both observational and theoretical research. One of the most exciting prospects in the study of Cygnus X-1 is the potential to discover new insights into the behavior of matter and energy in the presence of extreme gravitational fields. The conditions near the event horizon of a black hole are some of the most extreme in the universe, and Cygnus X-1 provides a rare opportunity to observe how matter behaves when subjected to these conditions. The accretion disk, made up of gas and dust pulled toward the black hole, emits intense radiation as it spirals inward, and the study of this radiation offers a window into the physical processes that occur in the extreme environment of the black hole's vicinity. One of the most fascinating aspects of this radiation is its ability to reveal information about the black hole's spin. Spin is a crucial property of black holes, and understanding how a black hole's spin interacts with the surrounding material is essential for building accurate models of their behavior. Cygnus X-1's accretion disk and the radiation it emits have allowed scientists to measure the spin of the black hole, offering important clues about its formation and the dynamics of the system. This spin is related to the angular momentum of the black hole, and studying how the disk and the black hole interact provides vital information about the nature of the singularity at the heart of the black hole. Furthermore, the relativistic jets emitted by Cygnus X-1 add another layer of complexity to the study of this system. These jets, which consist of high-energy particles traveling at nearly the speed of light, are ejected from the region around the black hole's event horizon. The exact mechanism behind the formation of these jets is still not fully understood, but they are thought to be closely linked to the black hole's spin and the accretion disk's behavior. The study of these jets, particularly their structure, composition, and how they interact with the surrounding medium, is a key area of research. As scientists continue to observe the behavior of the jets in Cygnus X-1, they are learning more about how relativistic jets are produced in general, and how these jets influence the evolution of galaxies and the surrounding interstellar medium. Cygnus X-1's role in understanding relativistic jets also ties into a larger question about the role of black holes in galactic evolution. Black holes, particularly supermassive ones at the centers of galaxies, are believed to have a significant impact on the development of their host galaxies. Cygnus X-1, being a stellar mass black hole, offers an analog for understanding the processes that may occur around supermassive black holes. The dynamics of accretion, radiation, and jet formation observed in Cygnus X-1 could provide valuable insights into the workings of supermassive black holes and how they interact with their host galaxies. As we delve deeper into the study of Cygnus X-1, the question of its ultimate fate arises. Like all stars, the companion star in the Cygnus X-1 system will eventually exhaust its nuclear fuel and undergo changes that could influence the entire system. In the case of the companion star, this process will likely lead to a supernova explosion, an event that could either leave behind a neutron star or, in the most extreme case, lead to the creation of another black hole. The fate of the companion star and its ultimate interaction with Cygnus X-1's black hole are critical for understanding the long-term evolution of this system and the role that stellar mass black holes play in the cosmic landscape. The ongoing study of Cygnus X-1 provides a powerful tool for exploring the fundamental questions of astrophysics. As the system continues to evolve, so too will our understanding of the processes that govern the behavior of black holes, from their formation to their interactions with the surrounding material. The ultimate goal is to answer the fundamental question of how black holes form, evolve, and influence the galaxies they inhabit. By studying Cygnus X-1, scientists are working to unlock the secrets of these mysterious objects and gain a deeper understanding of the nature of the universe itself. Beyond its importance as a research object, Cygnus X-1 has also captured the imagination of the public, inspiring countless discussions and debates about the nature of black holes and the mysteries of the universe. Its role in popularizing the study of black holes cannot be overstated. Over the years, the discovery of Cygnus X-1 has helped to bring black holes into the public consciousness, fueling interest in space exploration and inspiring the next generation of scientists and astronomers. It stands as a symbol of humanity's curiosity and determination to understand the unknown, a testament to our unyielding drive to push the boundaries of knowledge. Cygnus X-1 is more than just a black hole. It is a key to unlocking some of the most profound mysteries of the universe. From the study of its accretion disk and relativistic jets to its role in the broader context of black hole physics and galactic evolution, Cygnus X-1 remains one of the most important and intriguing objects in the sky. Its continued study promises to yield groundbreaking discoveries that will shape our understanding of the cosmos for years to come. As technology advances and new observational techniques come online, we are certain to uncover even more about this remarkable system and the role it plays in the grand cosmic narrative. The journey to understanding Cygnus X-1 is far from over, and as we continue to explore this enigmatic black hole, we will continue to uncover the mysteries of the universe itself. Cygnus X-1 remains a profound object of study, not just for its own scientific intrigue but also for its role as a crucial bridge to understanding the larger framework of astrophysical phenomena. As we continue to explore this black hole system, its relevance stretches far beyond its immediate surroundings, reaching into the heart of fundamental questions about how the universe works at its most extreme levels. It has provided insights into the behavior of matter under intense gravitational and relativistic conditions, insights that challenge and expand our understanding of physical laws. One of the major milestones in the study of Cygnus X-1 came with the measurement of the mass of its central black hole. In the early stages of observation, Cygnus X-1's nature as a black hole was debated, but as more data became available, particularly in the form of precise measurements of the orbital dynamics of the companion star, the black hole's mass was estimated to be roughly 15 solar masses. This value was confirmed by various methods, including X-ray observations that tracked the movement of material being pulled toward the black hole. Cygnus X-1 is classified as a stellar mass black hole, meaning it was formed from the collapse of a massive star, unlike the supermassive black holes found at the centers of galaxies, which are millions to billions of times the mass of the Sun. The fact that Cygnus X-1 is one of the first black holes to have had its mass accurately measured makes it a landmark in astrophysical research. The way in which its mass was determined was a combination of both indirect and direct methods. One such method involved examining the motion of the companion star, which orbits around the black hole in a predictable manner. By analyzing the gravitational influence of the black hole on the companion star, scientists were able to calculate the black hole's mass with great accuracy. These measurements are crucial for understanding the mass range of stellar mass black holes and contribute to our knowledge of how these objects form. Another significant aspect of Cygnus X-1 is the environment surrounding it, which is a hotbed of high-energy phenomena. The accretion disk around the black hole is an intense source of X-rays, produced as material from the companion star is drawn toward the event horizon. As matter falls into the black hole, it is compressed and heated to extremely high temperatures, reaching millions of degrees. This process generates X-rays, which are then detected by telescopes like the Chandra X-ray Observatory and the European Space Agency's XMM Newton. These X-rays are the primary way in which astronomers study the behavior of black holes, as they provide critical information about the material and processes occurring near the event horizon. The structure of the accretion disk itself is a point of great interest. While material is drawn toward the black hole, it doesn't fall in immediately. Instead, the material spirals inward, forming a hot, rotating disk. The matter at the innermost part of the disk moves at velocities approaching the speed of light, causing relativistic effects. The study of this behavior allows scientists to probe the properties of the black hole, including its spin and the rate at which it is consuming matter. The exact processes that occur in the inner regions of the accretion disk remain a topic of intense study, with questions about how matter behaves in the presence of such strong gravitational fields remaining open. The relativistic jets associated with Cygnus X-1 are another captivating feature of the system. These jets are streams of high-energy particles that are ejected from the region around the black hole at near light speeds. While much is still unknown about the mechanics of jet formation, it is believed that the black hole's spin, combined with the magnetic fields in the accretion disk, plays a crucial role in the production of these jets. These jets can extend thousands of light years into space, and their study is critical for understanding how black holes interact with their environments. Cygnus X-1, as a stellar mass black hole, provides an excellent analog for studying jet formation processes, which are also observed around supermassive black holes. These jets are fascinating not only for their high velocity but also for their role in the broader cosmic ecosystem. As they travel outward from the black hole, they can influence the surrounding gas and dust, even affecting the formation of new stars. The material expelled by the jets can carry significant energy away from the black hole system, which ultimately affects the dynamics of the surrounding interstellar medium. In a sense, these jets act as a mechanism by which black holes can shape their cosmic neighborhoods. Cygnus X-1 also serves as an important testbed for Einstein's theory of general relativity. In fact, one of the key pieces of evidence that led scientists to confirm that Cygnus X-1 is a black hole came from its ability to bend light. General relativity predicts that the intense gravitational field of a black hole would warp spacetime to such an extent that it can bend the path of light. This effect, known as gravitational lensing, has been observed in many other black holes, but Cygnus X-1's ability to warp light from a distant star provides a clear confirmation of this theory in action. While general relativity provides an excellent framework for understanding the gravitational behavior of black holes, there are still many unanswered questions when it comes to the nature of the singularity at the heart of a black hole. The singularity, a point where gravity becomes infinitely strong and the laws of physics as we know them break down, presents a paradox. This is where quantum mechanics, the theory that governs the behavior of the very small, seems to clash with general relativity, which governs the behavior of the very large. Cygnus X-1 and other black holes serve as laboratories where scientists hope to reconcile these two pillars of modern physics. Theoretical physicists continue to work on frameworks like quantum gravity, string theory, and loop quantum gravity, which may eventually provide insights into the true nature of black hole singularities. Moreover, Cygnus X-1 is valuable in the study of the life cycle of stars. The companion star in the system is a massive blue supergiant, which means it is at the end of its life cycle. It will eventually undergo a supernova explosion, a process that will likely result in the formation of either a neutron star or another black hole. The outcome of this explosion will depend on the mass of the companion star and the dynamics of the system. If the supernova is particularly violent, it could lead to the formation of another black hole, potentially setting up a scenario in which the two black holes might eventually merge. This possibility has profound implications for understanding the formation of binary black hole systems, a topic that has garnered significant attention in recent years. The fate of Cygnus X-1's companion star is a subject of much speculation and debate among astronomers. While it is impossible to predict the exact outcome of the star's supernova explosion, it is likely that the system will undergo dramatic changes. If the companion star does end up forming another black hole, this could lead to the formation of an even more massive binary black hole system. The merger of two black holes in such a system would release an enormous amount of energy in the form of gravitational waves, ripples in spacetime that were first predicted by Einstein's theory of general relativity and later directly observed by the LIGO and Virgo collaborations. The study of Cygnus X-1 has also contributed to our understanding of stellar evolution and the formation of black holes in general. Observing how the system's stars interact and evolve over time gives astronomers valuable clues about the processes that govern the birth and death of stars. In particular, Cygnus X-1 provides an example of a system in which a massive star collapses into a black hole, leaving behind a compact, highly energetic object that continues to interact with its companion. This process of stellar collapse and black hole formation is an important part of the larger picture of how stars, galaxies, and black holes are interconnected within the cosmos. In addition to its scientific value, Cygnus X-1 has also captured the imagination of the public, thanks to its mysterious and awe-inspiring nature. For many people, the concept of a black hole, an object with such intense gravity that not even light can escape it, is a fascinating and somewhat terrifying thought. Cygnus X-1, as one of the first black holes to be discovered, plays a key role in our understanding of these enigmatic objects. Its discovery marked a turning point in astrophysics, signaling the beginning of a new era in which black holes became a focus of scientific research. As we look to the future, Cygnus X-1 will continue to be a source of intrigue and discovery. Advances in telescope technology, such as the Event Horizon Telescope and the James Webb Space Telescope, will allow us to observe black holes with unprecedented detail. These observations will not only provide new insights into Cygnus X-1 but also help to expand our understanding of the broader black hole population. As we learn more about Cygnus X-1, we will be able to refine our models of black hole behavior and improve our understanding of how they form, evolve, and interact with their environments. Cygnus X-1 is a testament to the power of scientific discovery. Through decades of observation and research, it has provided us with a wealth of knowledge about one of the universe's most mysterious and fascinating phenomena. From its early days as an enigmatic X-ray source to its current status as a crucial object of study, Cygnus X-1 has shaped our understanding of black holes and continues to push the boundaries of what we know about the cosmos. Cygnus X-1's continuing role in astrophysical research serves as a reminder of how far humanity has come in its exploration of the universe. Once thought of as just a curious speck in the night sky, this system has become one of the most well-studied and important objects in modern astronomy. The insights gleaned from Cygnus X-1 not only enhance our understanding of black holes, but they also inform our broader comprehension of the cosmos. One of the key aspects of Cygnus X-1 that has drawn significant attention is the way in which it challenges and refines existing theories about gravity and relativistic physics. As the study of this system has progressed, it has served as an invaluable testing ground for Einstein's theory of general relativity, especially as it pertains to the behavior of spacetime near a black hole. The immense gravity around Cygnus X-1 distorts light and space in ways that continue to defy easy explanation, providing evidence that helps physicists refine their models of the universe at its most extreme scales. The idea that Cygnus X-1 might be playing a pivotal role in shaping our understanding of the very fabric of spacetime is an exciting one. As we develop better observational tools, such as the Laser Interferometer Gravitational Wave Observatory, LIGO, which has already detected gravitational waves from black hole mergers, we may one day be able to observe the behavior of matter and energy near the event horizon of Cygnus X-1 in real time. This would provide a much deeper understanding of the mechanics of accretion disks, relativistic jets, and the singularity itself. Such advancements could eventually answer some of the most profound questions in astrophysics, such as the nature of quantum gravity, the ultimate fate of black holes, and the possibility of multidimensional spacetime. Cygnus X-1 also contributes to our broader understanding of the evolution of galaxies. As we look at the interactions between black holes and their environments, we begin to see how these cosmic giants shape the structure and life cycle of galaxies. Black holes, both stellar mass and supermassive, play a central role in the dynamics of galaxy formation and evolution. Cygnus X-1, as a stellar mass black hole in a binary system, provides an important analog for the study of black holes in a variety of galactic contexts. Understanding how this black hole interacts with its companion star and the surrounding interstellar medium can provide clues to the role black holes play in regulating star formation and energy production within galaxies. The black hole's accretion disk, a swirling whirlpool of matter falling toward the singularity, remains one of the most intriguing aspects of Cygnus X-1. The gas and dust in the disk are heated to such extreme temperatures that they emit powerful X-rays, allowing astronomers to study their behavior in detail. What makes these accretion disks especially fascinating is the way they reveal the interplay between general relativity, thermodynamics, and magnetohydrodynamics. Matter in the innermost regions of the accretion disk experiences gravitational forces so intense that it accelerates to relativistic speeds. As it spirals inward, the matter is compressed and heated to millions of degrees, producing X-rays and gamma rays. This violent interaction between the black hole's immense gravity and the surrounding material offers a window into the very nature of spacetime, pushing the limits of our understanding of physics. The fact that we are able to study such an extreme and dynamic environment is a testament to the advancements made in observational technology. Telescopes that can detect X-rays, such as the Chandra X-ray Observatory, the XMM Newton, and the NICER, Neutron Star Interior Composition Explorer, have made it possible for scientists to observe the high-energy processes taking place in the vicinity of Cygnus X-1. By using these tools, astronomers have been able to refine models of accretion disk structure, black hole spin, and even the behavior of relativistic jets, enhancing our understanding of these mysterious cosmic objects. The phenomenon of relativistic jets is perhaps one of the most visually striking and mysterious aspects of Cygnus X-1. These jets, which are ejected from the poles of the black hole at nearly the speed of light, are not just fascinating in their own right, but they are also essential for understanding the broader cosmic environment in which black holes exist. As these jets extend for thousands of light years into space, they play an important role in regulating the interstellar medium, transferring energy across vast distances, and even influencing the formation of new stars. By studying Cygnus X-1's jets, scientists are uncovering how black holes interact with their surroundings in complex, and sometimes unexpected ways. These interactions provide valuable insights into how black holes, regardless of their size, can influence the larger structures of galaxies and even the evolution of the universe itself. Cygnus X-1 also offers key insights into the extreme states of matter that exist near black holes. The temperatures and pressures found near the event horizon are so high that they provide a unique environment for studying the behavior of matter under extreme conditions. Physicists are particularly interested in understanding how the material surrounding the black hole behaves in ways that are not fully explained by conventional models of physics. For instance, at the high velocities found in the accretion disk, relativistic effects come into play, resulting in phenomena like time dilation and the bending of light. The closer matter gets to the event horizon, the more extreme these relativistic effects become, offering an opportunity to test general relativity in conditions that would be impossible to recreate on Earth. Cygnus X-1's behavior has also led to important discoveries about the formation of black holes and binary systems. As scientists continue to study the system, they gain a better understanding of the conditions required for the formation of black holes in the first place. Stellar mass black holes, like the one at the center of Cygnus X-1, are thought to form from the collapse of massive stars. However, the exact mechanism by which this collapse occurs is still a subject of research. Cygnus X-1 serves as a real-world example of this process, allowing scientists to study how a massive star's core collapses into a black hole, while the outer layers of the star are either blown away or accreted by the black hole itself. This process of star formation, death, and rebirth is one of the most fascinating and important aspects of stellar astrophysics. In addition to its relevance in black hole physics, Cygnus X-1 holds a unique place in the history of observational astronomy. When it was first discovered in 1964, it was one of the first strong X-ray sources to be identified in the sky. Its discovery marked the beginning of an entirely new era in astrophysics, one in which high-energy phenomena, previously invisible to the naked eye, could be observed and studied in great detail. The discovery of Cygnus X-1 opened up a whole new field of study, known as X-ray astronomy, which has since led to the identification of hundreds of other black holes, neutron stars, and other exotic objects in the universe. What makes Cygnus X-1 even more special is its connection to the legacy of the legendary physicist, Stephen Hawking. Cygnus X-1 was one of the primary subjects of his work on the nature of black holes and his formulation of the laws of black hole thermodynamics. Hawking's contributions to the study of black holes, including his prediction of Hawking radiation, were groundbreaking. His work demonstrated that black holes are not completely black but instead emit a faint radiation due to quantum effects near the event horizon. This theoretical prediction has yet to be observed, but it has inspired a great deal of research into the quantum nature of black holes, with Cygnus X-1 serving as a key object for testing such theories. Looking toward the future, Cygnus X-1 will continue to serve as an invaluable laboratory for astrophysicists, providing insights into the fundamental nature of space, time, and matter. New advancements in observational technology, such as the construction of the James Webb Space Telescope and future gravitational wave detectors, will allow scientists to study black holes with unprecedented detail. In addition, advancements in theoretical physics, such as the development of quantum gravity and unified theories of physics, may one day allow us to understand the full nature of black holes and their role in the universe. Cygnus X-1's legacy is far-reaching, not only as a scientific milestone but also as an iconic symbol of the human quest for knowledge. Its discovery, study, and continued observation provide a window into the most extreme and fascinating phenomena in the universe, offering a glimpse of the forces that shape the very fabric of space and time. As we continue to explore and understand this black hole, we are drawn ever closer to the profound mysteries that lie at the heart of the cosmos. The ongoing research into Cygnus X-1 ensures that it will remain at the forefront of astrophysical exploration for years to come, continuing to inspire and challenge the next generation of scientists, astronomers, and physicists. In the ever-evolving study of Cygnus X-1, perhaps one of the most remarkable developments is the increasing precision with which we can measure its properties. Technological advancements have made it possible to determine its mass, distance, and spin with unprecedented accuracy. The black hole in Cygnus X-1 is now estimated to be about 21 times the mass of the Sun, and it spins at nearly the maximum rate allowed by the laws of physics. This rapid spin not only influences how matter behaves near the event horizon but also determines how much energy can be extracted from the black hole through processes like the Penrose mechanism or Blanford's Nagic process, both of which involve tapping into the rotational energy of a spinning black hole. The nearly maximal spin of Cygnus X-1 opens doors to a realm of physics where time and space become deeply intertwined. Near a spinning black hole, the effect known as frame dragging occurs. Space-time itself is twisted around the black hole's axis of rotation. This phenomenon is not just a theoretical curiosity but a measurable effect, and studying it in systems like Cygnus X-1 helps confirm predictions made by general relativity. Furthermore, frame dragging influences the orbits of particles in the accretion disk, the behavior of magnetic fields, and the dynamics of relativistic jets, making it a key component in the black hole's interaction with its surroundings. This interaction extends to the black hole's binary companion, the massive blue supergiant star HD 226868. The gravitational dance between these two objects is not just a spectacle of cosmic proportions, it's also a crucial laboratory for understanding tidal forces, angular momentum exchange, and stellar evolution. The companion star is gradually being stripped of its outer layers by the black hole's gravitational pull, feeding the accretion disk and powering the X-ray emissions that first revealed Cygnus X-1's presence. This mass transfer is not only changing the structure of the star but also altering the orbital dynamics of the entire system, leading to observable variations in X-ray luminosity and periodic shifts in the emitted spectrum. In a broader context, the study of systems like Cygnus X-1 feeds directly into our understanding of stellar death and the life cycle of binary systems. As more black hole binaries are discovered and studied, patterns begin to emerge, in their mass distributions, spin rates, and formation histories. These patterns help astronomers refine models of stellar evolution and collapse. For instance, Cygnus X-1 provides compelling evidence that some black holes can form without a visible supernova explosion. This so-called failed supernova scenario implies that massive stars can collapse directly into black holes in a relatively quiet manner, a theory with significant implications for population synthesis models and the predicted number of black holes in the Milky Way. Moreover, the gravitational environment around Cygnus X-1 enables unique insights into the behavior of matter under relativistic conditions. Gas in the inner accretion disk orbits at significant fractions of the speed of light, creating Doppler-shifted emissions and broadened spectral lines that allow scientists to map the velocity and distribution of the plasma. Observing these shifts over time not only reveals details about the black hole's immediate surroundings but also helps construct detailed models of the accretion process itself, from the outer disk to the plunge region at the edge of the event horizon. These models are increasingly sophisticated, incorporating not only gravity and radiation but also the effects of magnetic turbulence and viscosity. Magnetic fields are thought to play a key role in transporting angular momentum outward in the disk, allowing matter to spiral inward. This process, governed by the magnetorotational instability, MRI, is essential to the accretion process and is believed to be responsible for the structure and variability of the disk. Observations of flickering, flaring, and quasi-periodic oscillations in the X-ray light from Cygnus X-1 help test these theoretical models and connect them to real astrophysical behavior. Even the relativistic jets launched from Cygnus X-1 are tied to magnetic processes. These narrow beams of charged particles are likely powered by the twisting of magnetic field lines in the inner disk, coupled with the black hole's rotation. The details of how these jets form, what accelerates them, and how they remain collimated over vast distances are still open questions in astrophysics. But Cygnus X-1, with its well-studied jets, is a crucial data point in unraveling these mysteries. Jets from Cygnus X-1 have been observed to extend for several light-years, illuminating the interstellar medium and providing a trail of evidence for their powerful origins. The system's location within our galaxy also makes it an ideal target for long-term observation. Unlike more distant black holes in other galaxies, Cygnus X-1 lies within the Milky Way, approximately 7,200 light-years from Earth, in the constellation Cygnus. This relative proximity means that subtle changes in its X-ray brightness, jet activity, and stellar wind interactions can be monitored continuously and in great detail. Ground-based and space-based telescopes alike can study it over decades, building a comprehensive picture of a black hole's behavior over time. Cygnus X-1 is also becoming a cornerstone in the multi-messenger approach to astronomy. While it hasn't been the source of gravitational waves detected so far, its properties inform predictions about what kinds of signals we might expect from similar systems undergoing black hole mergers. Future generations of detectors, both terrestrial and space-based, could capture signals from black hole binaries in earlier evolutionary stages, or even directly from systems like Cygnus X-1 if its black hole were ever to merge with another compact object. The educational and cultural impact of Cygnus X-1 shouldn't be underestimated either. It has inspired generations of scientists, appeared in science fiction, and even been referenced in popular music and literature. Its mystique as one of the first black holes confirmed by observation makes it a powerful symbol of cosmic discovery. More than just a physical object, Cygnus X-1 represents a profound turning point in our quest to understand the universe, when speculation about black holes transformed into empirical science. As research continues, Cygnus X-1 will likely serve as a benchmark system for comparing new discoveries. Whether it's refining measurements of black hole spin, tracking changes in mass accretion rates, or modeling the behavior of matter near the event horizon, Cygnus X-1 remains central to the field. Every new observation made about this system brings with it fresh questions, and the possibility of deeper insights into the most powerful and enigmatic objects in the cosmos. The future study of Cygnus X-1 is poised to benefit from the next wave of astronomical technology. Projects like the James Webb Space Telescope, JWST, the European Extremely Large Telescope, ELT, the Square Kilometre Array, (SK), and NASA's Lynx X-ray Observatory aim to deliver even more precise data about stellar and black hole systems. In particular, Lynx and Athena, with their advanced X-ray capabilities, are expected to probe the hot gas dynamics in and around systems like Cygnus X-1 with sharper resolution and increased sensitivity. With these tools, scientists hope to dissect the inner structure of the accretion disk, investigate how energy is transferred within the disk, and examine the base of the relativistic jets where they are launched near the event horizon. One critical area of future study is understanding the detailed mechanism behind the relativistic jet formation. While it's widely accepted that rotating magnetic fields interacting with the black hole's spin power these jets, the precise way in which energy is extracted and converted into powerful, directed beams of plasma remains an active field of research. Cygnus X-1, with its continuous jet activity and well-characterized spin, serves as a near-ideal laboratory. Observations of its jets and radio wavelengths already offer clues, revealing how they precess, fluctuate, and interact with interstellar material. Future studies may uncover whether the jet's direction changes subtly over time due to changes in the inner accretion disk, or even as a result of lens-stirring precession, another relativistic effect of frame dragging caused by the black hole's intense spin. Another fascinating mystery surrounding Cygnus X-1 is the evolutionary fate of its companion star, HD 226868. As the black hole siphons off the massive star's outer layers through gravitational pull, the star itself is being stripped down to its core. Eventually, this blue supergiant is expected to end its life in a core collapse supernova, unless it too collapses directly into a black hole without a visible explosion, as many theories predict. If that happens, Cygnus X-1 could become a double black hole system, orbiting each other for millions or billions of years until they eventually merge. Such a merger would release an intense burst of gravitational waves, possibly detectable by future gravitational wave observatories like LISA, Laser Interferometer Space Antenna, providing yet another chapter in the saga of this legendary system. In fact, this potential black hole merger could be one of the most valuable natural laboratories for testing Einstein's general theory of relativity under extreme conditions. The merging of two black holes with known masses, spins, and orbital histories would allow astrophysicists to compare predicted waveforms against actual gravitational wave data, confirming or challenging our understanding of the laws of physics at their most fundamental level. Cygnus X-1 may, therefore, not only be part of our astronomical past, as one of the first black holes ever discovered, but also an integral part of our observational future. The high-energy phenomena associated with Cygnus X-1 also shed light on a broader cosmic question: how do black holes influence their galactic environment? Though stellar mass black holes like Cygnus X-1 are not as powerful as their supermassive cousins, they still inject enormous amounts of energy into the interstellar medium. The jets and winds from the system push against nearby gas and dust, heating it, compressing it, or dispersing it. Over long periods, this feedback can regulate the formation of new stars or even clear out entire regions of gas that might otherwise have collapsed into stellar nurseries. Studying this feedback loop helps scientists understand galaxy evolution on a large scale, how small-scale objects like Cygnus X-1 can have large-scale consequences. Another area of ongoing research is the magnetic field structure within the Cygnus X-1 system. Magnetic fields are notoriously difficult to measure directly in astrophysical environments, but their presence is inferred through polarization of light, synchrotron radiation from jets, and fluctuations in X-ray emission. Observations of polarized X-rays, particularly with missions like NASA's Imaging X-ray Polarimetry Explorer, IXP, help map the geometry of these fields. The way light is polarized as it emerges from the inner disk or is scattered by plasma near the black hole provides clues about the orientation and strength of the magnetic fields, which in turn govern how material accretes and how jets are launched. Cygnus X-1 also plays a role in refining stellar mass black hole formation theories across the universe. As gravitational wave observatories detect increasing numbers of black hole mergers, the need to understand their birth processes becomes more important. By closely studying systems like Cygnus X-1, where we know the masses, spins, companion characteristics, and orbital parameters, we create reference points to validate population synthesis models. These models predict how often black holes of certain masses form, how likely they are to be in binaries, and what types of supernovae or collapses produce them. Without empirical benchmarks like Cygnus X-1, these predictions remain speculative. Interestingly, Cygnus X-1's discovery and continued observation also reflect humanity's growing ability to see the invisible. Black holes, by definition, do not emit light. Their presence must be inferred through their effects, gravitational, electromagnetic, or otherwise. When Cygnus X-1 was first identified, the very concept of seeing a black hole was still controversial. But now, with radio telescopes imaging black hole shadows, like the Event Horizon Telescope did with M87, X-ray satellites capturing inner disk emissions, and gravitational wave detectors hearing the mergers of these objects, black holes have gone from hypothetical oddities to tangible, observable phenomena. Cygnus X-1 was the gateway to this transformation, the first real proof that black holes were not just mathematical curiosities but real, physical entities with measurable properties. Even philosophically, Cygnus X-1 invites reflection. The very notion that a star, once a bright, burning sphere of hydrogen fusion, could end its life as an object so dense that not even light can escape, is both awe-inspiring and humbling. The idea that this object, though invisible, exerts such a powerful influence on its environment and partner star, forces us to expand our notions of reality, existence, and the observable universe. Cygnus X-1 has become not just a physical object but a symbol of what science can uncover, of how far human understanding can reach, and of the mysteries that remain. And yet, despite decades of study, Cygnus X-1 continues to surprise. Subtle changes in its X-ray emissions suggest complex dynamics at play in the inner disk. Sudden increases in brightness, known as flares, can signal rapid rearrangements of magnetic fields, mini explosions of relativistic particles, or the brief visibility of structures near the event horizon. These transient phenomena are not only scientifically rich, they're also visually dramatic, capturing the imagination of the public and scientists alike. Monitoring these flares in real time helps refine theoretical models and opens the door to predictive astronomy, where machine learning algorithms could one day forecast black hole behavior. The continued fascination with Cygnus X-1 also fuels a larger cultural and educational mission. Students learning about black holes today almost always encounter Cygnus X-1 early in their education. Its name has appeared in everything from astronomy textbooks to rock lyrics. It was famously referenced by the progressive rock band Rush in a two-part song exploring the philosophical and cosmic implications of such an object. Popular documentaries and science programs frequently showcase Cygnus X-1 when explaining black hole physics, using it as the archetypal example of a stellar mass black hole in action. In this way, Cygnus X-1 serves not only as a scientific subject but as a gateway to broader public interest in astrophysics and cosmology. All of this, the observation, the theory, the culture, the future, revolves around a single, distant object in the constellation of Cygnus. A dark point in space, invisible to the human eye, but glowing brightly in the X-ray sky. An object born from the death of a massive star, quietly pulling in matter and reshaping everything around it. Cygnus X-1 remains a cosmic enigma, partially revealed, deeply influential, and endlessly compelling. The tale of Cygnus X-1 is, in many ways, a story of extremes. It's an object born from the most violent processes in the universe, the collapse of a star so massive that it left behind not even a neutron star, but a singularity cloaked in an event horizon. And yet, despite its silent, invisible nature, Cygnus X-1 screams across the cosmos in high-energy X-rays, as if the universe is unwilling to let it remain hidden. Its influence ripples outward, dragging matter into a luminous spiral, heating it to millions of degrees, spitting out beams of particles at nearly the speed of light. And all the while, it silently devours the light, mass, and energy it draws in, leaving only its gravitational fingerprint and a cascade of radiation as evidence of its presence. The black hole itself, thought to be around 21 solar masses, challenges previous assumptions about how such objects form. Earlier models predicted stellar mass black holes should not commonly exceed 15 solar masses, especially in binary systems where supernova explosions can be asymmetric and eject matter violently. Yet Cygnus X-1 stands as a reminder that our models are only as strong as the evidence we gather. Its mass and spin, measured with increasing precision using relativistic modeling of X-ray spectra and orbital mechanics, suggests that it may have formed in a relatively direct collapse, a scenario where a massive star implodes without a spectacular supernova, quietly creating a black hole without disrupting the surrounding binary system. This has critical implications for how we understand the formation of compact object binaries, especially those that eventually merge to produce detectable gravitational waves. This quiet formation also likely helped preserve the wide but stable orbit between Cygnus X-1 and its massive blue supergiant companion, HD 226868. This star, still fusing elements in its core, continues to live out a luminous but turbulent life, shedding material that is captured by the black hole's immense gravity. This results in the formation of a warped, seething accretion disk, a dynamic ring of gas that spirals inward, heating due to friction and magnetic turbulence. The physics of this disk is one of the most complex and fascinating arenas in astrophysics. It is governed by principles of magnetohydrodynamics, general relativity, and plasma physics. Tiny differences in temperature or density within the disk can give rise to instabilities, magnetic reconnection events, and shock waves. These, in turn, generate the X-ray variability that we observe from Earth. The X-rays from Cygnus X-1 are not just emissions of heat, they are the signatures of extreme processes occurring in strong gravity. By studying the way X-rays flicker and fluctuate over milliseconds to days, scientists can infer what's happening just kilometers away from the black hole's event horizon. This region, known as the innermost stable circular orbit, ISCO, is the last, safe, orbit for matter before it plunges into the black hole. Its radius depends on the black hole's spin, and for Cygnus X-1, that spin is near maximal. This suggests that the black hole has been spinning rapidly since its birth, or has been spun up over millions of years by accreting matter from its companion. Spin is a crucial property because it determines the efficiency with which the black hole can convert mass into energy. A spinning black hole can theoretically convert as much as 42% of the mass it accretes into energy, making it one of the most efficient engines in the universe. That energy doesn't simply vanish. Some of it escapes as X-rays, while some may be funneled into powerful jets launched perpendicular to the disk. These jets are made of charged particles accelerated to nearly the speed of light and held tightly in place by twisted magnetic fields. They shine in radio wavelengths and can travel vast distances across interstellar space. The mechanism behind jet formation remains one of the great unsolved problems in astrophysics. Does the energy come from the disk, or from the black hole's spin itself, extracted by a process like the Blandford's-Najek mechanism? In this process, magnetic field lines anchored in the accretion disk tap into the rotational energy of the black hole, converting it into the kinetic energy of the jet. Cygnus X-1 provides an ideal testing ground for such theories because it exhibits relatively steady jet activity and well-measured spin, allowing detailed comparisons between models and observations. Even more intriguing is the prospect of using polarization to peer into the geometry of these high-energy regions. Polarization describes the orientation of light waves and is influenced by the environment through which light travels. Instruments like NASA's IXP, Imaging X-ray Polarimetry Explorer, have begun measuring the X-ray polarization of sources like Cygnus X-1, helping to map the magnetic fields near the event horizon. These observations are shedding light, quite literally, on the invisible architecture of black hole systems, telling us how light is bent, scattered, and polarized by relativistic effects. Cygnus X-1 also continues to provide critical insight into the state changes of black holes. Over time, the system cycles between different modes of accretion, hard states, soft states, and intermediate states, each defined by the relative strength of the X-ray emissions at different energies. In the hard state, the X-rays are dominated by high-energy photons, likely produced in a corona of hot electrons above the disk. In the soft state, the emission is more thermal, originating from the disk itself. These transitions are linked to changes in the accretion rate, disk structure, and even jet activity. By tracking how Cygnus X-1 moves through these states, astrophysicists gain a deeper understanding of how black holes consume matter and regulate their emissions. Moreover, the binary nature of Cygnus X-1 adds another layer of complexity. As the black hole pulls matter from its companion, the balance of mass and angular momentum in the system changes. Over long timescales, this can cause the orbit to shrink, leading to an eventual merger, or, depending on mass loss, it could widen the orbit and lead to a more stable but less interactive system. Studying these dynamics in real time allows scientists to refine their models of binary evolution, which are crucial for predicting the population of black hole mergers that observatories like LIGO and Virgo detect. Beyond astrophysics, Cygnus X-1 has a broader cultural legacy. Its designation, simple, almost cryptic, evokes the romance of space discovery. Located in the Swan constellation, its name ties it to ancient mythology and celestial cartography. The designation, X-1, signifies it was the first X-ray source identified in its constellation, anchoring its place in scientific history. For many astronomers, Cygnus X-1 was the first black hole they learned about. For the public, it remains one of the few black holes that has achieved name recognition, joining the likes of Sagittarius A and M87. And for scientists, it is a constant companion, a system that continues to offer data, test theories, and defy complete understanding. Even now, as more sophisticated missions peer deeper into the X-ray sky, Cygnus X-1 remains a benchmark, a cosmic touchstone. It reminds us of what we've learned, and what we've yet to uncover. In its light, in its silence, in its dance with a dying star, it holds the keys to some of the most profound questions we can ask. What happens to time and space at the edge of a singularity? How do the most extreme forces in the universe shape the galaxies we live in? And can we, limited by distance and perception, ever fully understand the dark hearts of the cosmos? The journey of exploring Cygnus X-1 does not merely lead us into the heart of a black hole system. It draws us into the very structure of spacetime, into a place where our conventional understanding of physics begins to unravel. Cygnus X-1 is not just an astrophysical object, it is a cosmic paradox wrapped in data, light, and silence. Its study bridges the gap between theory and observation, between imagination and mathematical certainty, and between the grandeur of stellar evolution and the abyss of gravitational collapse. One of the most profound aspects of Cygnus X-1 lies in its role as a testbed for Einstein's theory of general relativity. The region around the black hole represents one of the most extreme gravitational fields accessible to observation. Light from the inner accretion disk is distorted as it climbs out of this gravity well, affected by both gravitational redshift and lensing. The very shape of the X-ray spectrum carries the fingerprints of relativistic effects, allowing scientists to test predictions of Einstein's equations in a regime that can't be replicated on Earth. For example, the iron K-alpha emission line, produced by fluorescence in the disk, gets broadened and skewed in ways that only occur near an event horizon. By modeling these distortions, scientists can extract details about the disk's geometry, the black hole's spin, and the inclination of the system. But the implications go even deeper. Cygnus X-1 enables tests of the no-hair theorem, the idea that black holes can be fully described by just three properties: mass, spin, and charge, the last of which is negligible for astrophysical black holes. If observational data from Cygnus X-1 were to show discrepancies from what general relativity predicts, it could suggest new physics, perhaps deviations from Einstein's theory, or hints at quantum gravitational effects. So far, however, Cygnus X-1 has passed these tests with flying colors, lending further credibility to general relativity even under the most extreme conditions imaginable. The environment around Cygnus X-1 is equally compelling. HD 226868, the blue supergiant companion star, is not just a passive partner in this binary system, it is a volatile, high-energy star in its own right. With a mass estimated around 40 times that of the Sun and a luminosity hundreds of thousands of times greater, it is a giant nearing the end of its own life. The stellar wind it produces is dense and fast, traveling at thousands of kilometers per second. Some of this material escapes into space, but much of it is gravitationally captured by the black hole, feeding the accretion disk. This process creates a complex, dynamic interaction zone where gas is shocked, heated, ionized, and sometimes ejected again. This region is ripe with questions. How stable is the accretion flow? What role do magnetic fields play in transporting angular momentum through the disk? How do instabilities in the disk lead to variations in X-ray emission? Observing these changes, through long-term monitoring from space-based X-ray telescopes, has allowed researchers to construct increasingly detailed models of how matter behaves in this violent regime. Missions like RxD, NuSTAR, Chandra, and more recently, NICER and IXP, have provided hundreds of thousands of observations, each a tiny puzzle piece in the broader mosaic of understanding Cygnus X-1. Furthermore, there's an intriguing relativistic effect tied to Cygnus X-1's orbit known as precession. Because of the intense gravitational fields and possible asymmetries in mass distribution, the inner accretion disk can wobble over time, causing changes in the orientation of X-ray emission. This precession is not only a test of general relativity but also a window into the geometry and alignment of the disk, the black hole's spin axis, and the binary orbital plane. This is crucial because misalignment between the spin of the black hole and the orbit of the system could offer clues about how the black hole formed, whether in a direct collapse, or through an asymmetric supernova that might have kicked it into a tilted spin. Then there's the question of the jet. Though Cygnus X-1's jets are less powerful than those seen in other systems, such as microquasars like SS433 or GRS 1915+105, they still offer an important glimpse into the physics of relativistic outflows. The formation of these jets is intimately tied to the inner regions of the accretion disk, perhaps even to the black hole's ergosphere, a region just outside the event horizon where space itself is dragged around by the black hole's spin. Understanding how energy is extracted from this region and funneled into jets could help answer one of astrophysics' most enduring questions. How do black holes influence their environments, even across vast interstellar distances? In Cygnus X-1, we also see a powerful example of how binary systems evolve. The two stars that created this system likely began their lives as a pair of massive objects orbiting one another in a relatively tight binary. The more massive of the two evolved more quickly, exhausting its nuclear fuel and undergoing gravitational collapse. The presence of a close companion likely influenced this process, perhaps stripping mass from the star, altering its evolutionary path, and accelerating its death. Now, millions of years later, the tables have turned. The companion that once drew mass is now being devoured by the black hole it helped shape. This coevolution has implications for the future of the system as well. As HD 226868 continues to lose mass, it may eventually collapse into another compact object, a neutron star, or perhaps a second black hole. If that happens, and if the system remains gravitationally bound, Cygnus X-1 could one day become a binary black hole system. Over billions of years, gravitational radiation would cause the orbit to decay, ultimately leading to a cataclysmic merger and a burst of gravitational waves that could be detected across the cosmos. In this sense, Cygnus X-1 is not just a window into the past, it is a preview of the universe's future. This possibility ties Cygnus X-1 to another frontier of astrophysics, gravitational wave astronomy. Since the first detection of black hole mergers by LIGO in 2015, scientists have been searching for progenitor systems, binaries that could eventually evolve into those high-energy collisions. Cygnus X-1 is among the most promising candidates, and its well-characterized properties, mass, spin, orbital period, make it a perfect laboratory for modeling the end states of stellar evolution. By studying systems like Cygnus X-1 in detail, we can better predict the rates and characteristics of future gravitational wave events, and perhaps even forecast the signature of this system's eventual demise, billions of years from now. Even the environment around Cygnus X-1 bears signs of its influence. Observations in radio wavelengths have revealed a large lobe of gas surrounding the system, a bubble inflated, perhaps, by earlier episodes of jet activity or powerful winds from the supergiant. This structure, tens of light years across, speaks to the long-term impact that even a relatively small black hole can have on its surroundings. Over time, the energy injected into the interstellar medium can trigger star formation, disperse gas, and sculpt the structure of the galactic disk. Cygnus X-1, though only one black hole among billions, is a microcosm of the processes that shape galaxies. As we peer ever deeper into this system, new technologies and techniques promise to reveal even more. The next generation of X-ray observatories, such as Athena and Lynx, will offer higher resolution, better sensitivity, and broader energy coverage. Ground-based optical telescopes equipped with adaptive optics and interferometry will allow for even more precise measurements of the companion's properties and motion. And as gravitational wave detectors improve in sensitivity, we may eventually be able to hear the faint whispers of binary black holes before they merge, long before any explosion or burst of light signals their final act. And still, for all we've learned, Cygnus X-1 continues to elude complete understanding. It is a mystery that deepens as we study it, a paradox that becomes more complex the closer we get to the truth. Its X-rays shine across the cosmos, but they are only shadows of the deeper darkness within. In that sense, Cygnus X-1 is not just a black hole. It is a mirror, reflecting the limits of our knowledge and the unending quest to understand the cosmos. In this endless quest to decode the secrets of Cygnus X-1, the very fabric of inquiry begins to blend astrophysics with philosophy. We are not merely studying matter spiraling into oblivion. We are observing the ultimate test of what it means for information, energy, and existence to be swallowed by something we cannot touch, only infer. Cygnus X-1 forces us to ask questions that stretch beyond equations, questions about the nature of reality itself. At the core of the black hole lies the singularity, a point where density becomes infinite, and the laws of physics, as we know them, cease to function. It is here that general relativity breaks down, and quantum mechanics, despite its overwhelming success at small scales, provides no definitive answers. The singularity is not just a feature of theoretical models, it is the destination of matter that falls past the event horizon, an unseen point of no return. And yet, it remains forever hidden, cloaked by the very gravity it creates. This leads to the black hole information paradox, one of the most perplexing unresolved problems in modern physics. If information about the physical state of matter is lost when it crosses the event horizon, this contradicts a core principle of quantum mechanics: that information must be conserved. However, if information is not lost, then how does it escape a region from which nothing, not even light, can return? Cygnus X-1 doesn't directly solve this paradox, but it provides a context in which it becomes a living question. Observing how matter behaves near the event horizon, and how radiation carries subtle imprints of its journey, may one day offer clues. One intriguing possibility is that information escapes through a process called Hawking radiation, predicted by Stephen Hawking in the 1970s. This radiation arises from quantum effects near the event horizon, where particle-antiparticle pairs briefly emerge from the vacuum. One particle falls in, while the other escapes, slowly draining the black hole's mass over unimaginable timescales. Though Hawking radiation has never been directly observed, especially not from stellar-mass black holes like Cygnus X-1, it remains a key theoretical component in our effort to unify gravity and quantum mechanics. If we could somehow detect such emissions, even indirectly, Cygnus X-1 might become a cornerstone in the development of quantum gravity. Another layer of mystery involves time itself. According to general relativity, time slows near massive objects. At the edge of a black hole, this effect becomes extreme. From an outside observer's point of view, time for an object falling into the black hole appears to freeze at the event horizon. This leads to mind-bending interpretations of what it means for something to cross the threshold. Is the object truly gone? Is it smeared over the horizon? Could it be encoded holographically on the event horizon's surface, as some versions of the holographic principle suggest? The holographic principle, inspired by black hole thermodynamics and string theory, proposes that all the information contained within a volume of space can be represented by information encoded on its boundary. Applied to black holes, this suggests that everything that falls in is somehow preserved on the surface of the event horizon. If true, it would mean the universe itself may be a kind of hologram, with three-dimensional reality emerging from two-dimensional surfaces. Cygnus X-1, in this view, becomes more than an object. It becomes a gateway to reimagining space, time, and information. These ideas remain speculative, but they guide the frontiers of theoretical physics. Observational data from Cygnus X-1 may not yet be able to confirm or deny them outright, but it can constrain the space of possibilities. As our instruments grow more precise, they may reveal anomalies in the expected behavior of light, motion, or polarization, signatures that could point toward new physics. Yet despite its role as a crucible for high-level theory, Cygnus X-1 is also deeply connected to the observable cosmos. Its X-ray emissions help heat and ionize the interstellar medium, affecting the chemistry of nearby clouds. Its massive companion star enriches its surroundings with heavy elements through stellar winds. Over eons, these elements will be recycled into new stars, planets, and perhaps even life. The energy of death, in this sense, feeds the birth of the future. And even now, the story of Cygnus X-1 continues to evolve. Astronomers remain vigilant, watching for changes in brightness, shifts in spectral lines, and flickers of polarization. Each new piece of data adds a pixel to the image of this cosmic monster. The coming decades promise even more breakthroughs. With more sensitive detectors, longer observation campaigns, and increasingly sophisticated models, we may one day peer deeper into the shadows surrounding Cygnus X-1 and emerge with a clearer picture of the universe's most enigmatic force. For now, Cygnus X-1 remains a paradox, a source of both illumination and obscurity. It challenges our intellect, stirs our curiosity, and stands as a reminder that even in the age of advanced science, there are places where mystery still reigns. And as long as that mystery endures, so too does the journey, an unending pursuit of knowledge, driven by the gravitational pull not just of mass, but of wonder itself. In the relentless gravitational pull of curiosity that Cygnus X-1 exerts upon the scientific mind, we find ourselves compelled to delve deeper into not only its behavior, but its broader implications. The region of space that harbors Cygnus X-1 is not some detached, isolated arena. It exists within a dynamic celestial neighborhood, part of the Milky Way's rich and complex galactic structure. This positioning allows astronomers to study Cygnus X-1 within the context of galactic evolution and stellar population dynamics. The star-forming regions of the Cygnus constellation are particularly rich, and the presence of Cygnus X-1 serves as a reminder that even the most brilliant of stars may end their lives as silent sentinels of darkness. Cygnus X-1's interaction with its surrounding interstellar environment is a subject of immense interest. As material is accreted from the companion star into the black hole, it forms an accretion disk, a swirling maelstrom of gas heated to millions of degrees by gravitational compression and friction. This disk emits intense X-rays, which not only illuminate the system itself but impact the wider interstellar medium. The high-energy photons can ionize nearby gas, altering chemical pathways and potentially influencing star formation in the surrounding region. Such interactions offer a glimpse into the feedback mechanisms by which black holes, even stellar mass ones, shape their environments. Further, the variability in the X-ray output from Cygnus X-1 provides a diagnostic tool for probing conditions within the accretion disk. Rapid fluctuations in brightness suggest dynamic processes occurring near the event horizon, perhaps linked to magnetic turbulence, instabilities in the disk, or the effects of general relativistic frame dragging, a phenomenon where space-time itself is twisted by the rotation of the black hole. These moment-to-moment changes are like a symphony of high-energy activity, each flicker a coded message from a region where the very fabric of reality is stretched to its limits. In recent years, one of the most significant discoveries has been the measurement of the spin of the black hole in Cygnus X-1. Determining the spin parameter, essentially how fast the black hole is rotating, provides critical insight into its history. A rapidly spinning black hole suggests that it may have gained significant angular momentum either during its formation or through prolonged accretion from the companion star. In Cygnus X-1's case, measurements indicate it is spinning at near maximal speed, a fact that supports theories of its formation via a massive star collapsing directly into a black hole without a traditional supernova explosion. This finding also ties into larger questions about the mechanisms of black hole formation. Traditional models of stellar death often involve supernovae, cataclysmic explosions that scatter a star's outer layers into space. However, if Cygnus X-1 formed via direct collapse, it might have bypassed such an event entirely. This is not just a detail. It reshapes our understanding of the end-of-life pathways for the most massive stars. It also implies that the birth of some black holes may be relatively silent, without the dramatic flare we've come to associate with stellar death. Moreover, studying the spin and mass of Cygnus X-1 contributes to the evolving field of black hole demographics. By cataloging properties of known black holes, astronomers can begin to discern patterns: how mass relates to spin, how environment influences accretion, and how binary interactions evolve over millions of years. These statistical insights are essential not just for understanding Cygnus X-1, but for placing it within the broader context of galactic evolution and stellar population synthesis. Another layer of richness comes from the study of the optical and ultraviolet emissions from the companion star, HD 226868. This massive O-type supergiant is not a passive participant but an active player in the dance of cosmic gravity. Its powerful stellar wind feeds the accretion disk, and its close orbit around the black hole allows for precise measurements of orbital dynamics. The shape of its orbit, the gravitational redshift of its spectral lines, and the variations in brightness all provide a wealth of data about the mass of the black hole and the nature of the interaction between the two bodies. Additionally, the stellar wind from HD 226868 is not isotropic. It is focused toward the black hole by the immense gravitational gradient, forming a stream of material that is funneled into the accretion disk. This process is influenced by the Roche-Loeb geometry, the effective gravitational boundary between the two stars. The way material flows through this region provides valuable analogs for studying mass transfer in other binary systems, and can even inform our understanding of phenomena such as type Ia supernovae and the formation of neutron star binaries. As we continue to accumulate observational data, new technologies play a pivotal role. Missions like the Chandra X-ray Observatory, NuSTAR, and the upcoming Athena mission by the European Space Agency are designed to probe the high-energy universe with unprecedented sensitivity. These instruments allow for more detailed spectral analysis, better temporal resolution, and the potential to detect previously unseen features such as absorption lines from the accretion disk's inner regions. With each improvement in our tools, Cygnus X-1 reveals another layer of its cosmic narrative. Parallel to observations, theoretical modeling has advanced significantly. General relativistic magnetohydrodynamic (GRMHD) simulations allow scientists to recreate the conditions near the event horizon of black holes like Cygnus X-1 and Silico. These models simulate the behavior of magnetized plasma under the influence of intense gravity and relativistic effects. The resulting simulations not only match observed features like X-ray variability and disk morphology, but also predict behaviors yet to be confirmed observationally. These predictions, in turn, guide new observation campaigns and refine our understanding of black hole physics. But the impact of Cygnus X-1 extends beyond professional astronomy. It is a cultural icon, referenced in science fiction literature, television, and even music. Perhaps most famously, the progressive rock band Rush dedicated an entire suite, Cygnus X-1 Book I, The Voyage, to a fictional journey into the black hole. This artistic engagement with science underscores the profound human fascination with the unknown, the infinite, and the sublime. It reflects our innate desire not just to understand the universe but to find our place within it, even if that means confronting the terrifying beauty of a star that collapsed into eternal night. Indeed, this cultural resonance is part of what makes Cygnus X-1 such a compelling subject. It is not merely a point of light on a chart or a data set to be analyzed, it is a symbol. A symbol of how far we have come in our understanding of the cosmos, and how far we still have to go. From the early days of skepticism and debate to the modern era of relativistic astrophysics, Cygnus X-1 has accompanied us on a journey of intellectual expansion and emotional awe. As the black hole continues its slow, silent consumption of matter, we continue our rapid, noisy exploration of meaning. Every photon that escapes its gravitational grip carries with it a story, not just of mass and motion, but of possibility. And so we watch, we listen, we calculate, and we dream, knowing that in the heart of the constellation Cygnus, the universe is whispering secrets to those patient enough to hear them. As the accretion process continues within Cygnus X-1, we find ourselves increasingly fascinated by the seemingly eternal interaction between its black hole and its companion star. Over millions of years, this gravitational relationship will evolve, but even today, each moment provides astrophysicists with a cosmic laboratory, rich with data and riddled with puzzles. The very act of matter spiraling into the black hole is one of the most energy-efficient processes in the known universe, releasing vast amounts of X-ray radiation per unit of mass accreted. This makes Cygnus X-1 not only a beacon in the sky but also a benchmark for the study of accretion dynamics in extreme environments. This intense radiation has another important consequence. It affects the stellar wind of HD 226868. The powerful X-rays emitted by the hot inner regions of the accretion disk can photoionize the stellar wind, altering its structure and behavior. In essence, the black hole is sculpting the flow of material from the companion star. Observations have shown that the wind is not uniform. Rather, it is clumpy, with regions of higher and lower density, and the ionization by the X-rays can suppress or enhance these structures. Understanding these complexities is essential not only for studying Cygnus X-1 but for other high-mass X-ray binaries and their role in galactic ecology. Furthermore, the accretion disk itself is a source of great mystery and fascination. It is not simply a uniform disk of matter spiraling inwards. Rather, it contains a range of physical processes operating across multiple scales. At larger radii, viscosity and angular momentum transport dominate the evolution of material, while closer to the black hole, relativistic effects begin to significantly distort the motion and radiation of infalling gas. The inner regions of the disk may also be subject to warping or precession due to the lens stirring effect, an outcome of general relativity that causes the orbital plane of matter to precess around a spinning black hole. This precession, if present, could have implications for the periodicity of the X-ray emission and the orientation of any relativistic jets. While Cygnus X-1 is not the most prominent jet-producing system, there is evidence that it does exhibit a faint, compact radio jet, a telltale sign of material being launched at near-light speed along the rotational axis of the black hole. The presence of such jets links Cygnus X-1 to a broader class of objects known as microquasars, which mimic the behavior of distant quasars on a smaller, stellar scale. These jets are believed to be powered by the magnetic fields threading the accretion disk and tapping into the rotational energy of the black hole itself, possibly through a mechanism known as the Blandford-Znajec process. In addition to electromagnetic observations, Cygnus X-1 has become increasingly relevant in the era of gravitational wave astronomy. While it has not yet been a source of detected gravitational waves, its nature as a compact binary system places it within the realm of systems that may, in the distant future, merge and produce such ripples in spacetime. Its role, therefore, is educational and foundational. It helps refine our models of binary evolution, mass transfer, and the ultimate fate of such systems, feeding into our predictions for the kinds of gravitational wave events that observatories like LIGO and Virgo are designed to detect. This also raises the question of long-term evolution. What will become of Cygnus X-1? Over millions of years, the mass transfer may alter the masses of the components significantly. The black hole may grow, but more importantly, the companion star will evolve. As it exhausts its nuclear fuel, it may undergo its own collapse, potentially becoming a neutron star or even forming a second black hole. In such a scenario, we could eventually witness the birth of a double black hole binary system, prime candidates for future mergers detectable through gravitational waves. This evolutionary path is speculative but scientifically plausible, and it offers a captivating narrative of cosmic transformation. In the shorter term, the orbital dynamics of the system are closely monitored. The orbit is not circular but slightly elliptical, and the period is just under 6 days. This close proximity allows tidal forces to play a role in shaping the evolution of the system. Tidal interactions can transfer angular momentum between the star and the orbit, potentially leading to spin-orbit alignment or synchronization. These effects are subtle but can leave measurable imprints on the system's light curve, radial velocity variations, and spectral line profiles. Delving deeper into observational techniques, it's important to appreciate how multi-wavelength astronomy has enriched our understanding of Cygnus X-1. X-ray telescopes provide the most direct insight into the accretion processes, but radio observations trace the outflows and jets, while optical and ultraviolet studies focus on the companion star and its wind. Each wavelength band tells a different part of the story. High-resolution spectroscopy in the optical and ultraviolet reveals the Doppler shifts of the star's absorption lines, allowing astronomers to calculate orbital parameters and estimate the black hole's mass. These measurements are then combined with parallax data from missions like Gaia, which has greatly improved distance estimates to the system and, therefore, the intrinsic luminosity of its components. An even more nuanced layer of data comes from polarimetry, the measurement of the polarization of light. Polarization can reveal information about the geometry and alignment of scattering material in the system, such as the structure of the accretion disk or the presence of magnetic fields. In fact, Cygnus X-1 was one of the first black hole candidates for which polarization measurements provided indirect evidence for relativistic effects near the event horizon, reinforcing the interpretation of the compact object as a true black hole rather than some alternative exotic object. Another aspect deserving attention is the role of simulations and computer modeling in interpreting the flood of data from Cygnus X-1. Numerical simulations allow scientists to explore scenarios that are difficult or impossible to recreate in a laboratory. Using supercomputers, researchers can model the fluid dynamics of the accretion disk, the behavior of magnetic fields, the formation of jets, and the transfer of mass in binary systems. These simulations must incorporate the full suite of physical laws: gravity, magnetism, radiation transport, thermodynamics, and quantum processes, all governed by relativistic equations that become increasingly complex near the black hole. The match between simulation outputs and observed light curves or spectral features provides a test of our theories and often leads to the refinement of our understanding. The long history of Cygnus X-1's study also highlights the collaborative nature of astronomical science. Observations and insights have come from telescopes and institutions around the world, from high-energy X-ray observatories in orbit to ground-based optical telescopes in Chile, Hawaii, and the Canary Islands. Each dataset builds upon the previous, creating a layered, textured understanding of the system. And as each new generation of scientists brings fresh perspectives, new questions emerge. How does spin affect jet formation? Are there unrecognized feedback loops between radiation and stellar wind dynamics? Could the variability we observe be tied to yet undetected companions or longer-term cycles? In seeking answers, researchers are not just expanding our knowledge of one object but testing the fundamental physics that apply across the cosmos. Cygnus X-1 acts as a proving ground for theories of strong gravity, plasma behavior, radiation-matter interaction, and binary evolution. It is a system that forces us to grapple with extremes of mass, energy, density, and time. And still, amid the data and models, the system holds onto its mystique. Observing Cygnus X-1 is a bit like listening to an ancient, ever-changing melody, sometimes chaotic, sometimes harmonic, but always profound. It is both a lighthouse and a mirror, guiding our scientific journey and reflecting the relentless human pursuit of understanding. The light from Cygnus X-1, though it has traveled thousands of light years to reach us, is only a whisper of the tumult unfolding within its core. To imagine the system is to picture a massive, brilliant blue supergiant star eternally locked in a desperate gravitational dance with an invisible partner, a black hole siphoning its life away one stream of matter at a time. From afar, this celestial duet appears tranquil, but beneath its surface lies a churning engine of cosmic violence, where physics bends and breaks under the crushing weight of gravity. The beauty of Cygnus X-1 lies not only in its observable traits but also in the secrets it keeps, the mysteries it hints at, and the universal laws it allows us to probe. One of the most captivating aspects of Cygnus X-1 is the measurement of its spin. Among all known black holes, It is believed that Cygnus X-1 spins at a rate incredibly close to the speed of light. In relativistic terms, this means its dimensionless spin parameter is near the maximum theoretical limit, a equals 1. Spin plays a vital role in the physics of black holes. It influences the structure of the accretion disk, the geometry of the event horizon, and the potential for the system to launch jets. When astronomers calculate this spin, they rely on the X-ray spectra emitted by the hot inner accretion disk. The innermost stable circular orbit, ISCO, of the disk depends on the black hole's spin. Faster spins allow the disk to reach closer to the event horizon, heating the gas to higher temperatures and emitting more energetic X-rays. To extract this data, researchers use models based on general relativity and match them to the observed X-ray spectra, particularly focusing on the shape of the thermal continuum and the reflection features caused by X-rays bouncing off iron atoms in the disk. The iron K-alpha line, which appears at 6.4 keV in the rest frame, gets broadened and skewed due to the intense gravity and relativistic effects near the black hole. These distortions allow scientists to determine how close matter can orbit the black hole, which in turn constrains its spin. Cygnus X-1's near maximal spin hints at a violent origin. Perhaps it was born spinning rapidly from the start, during the collapse of its progenitor star. Or maybe it accumulated angular momentum over millions of years through the steady accretion of mass. This naturally leads to deeper questions about the formation and evolution of such a system. Was Cygnus X-1's black hole the end result of a single massive star's collapse? Or did it emerge through more complex interactions in a dense stellar cluster? Could it have gained mass and spin from a past merger or an ancient third companion now lost? These scenarios are not merely speculative. They drive theoretical work and simulations aimed at understanding stellar evolution and black hole demographics across the Milky Way. The environment around Cygnus X-1 also plays a significant role in shaping its observational features. It lies in the Cygnus OB3 association, a region rich with hot, young, massive stars. This stellar neighborhood influences the interstellar medium around Cygnus X-1, creating complex patterns of absorption and scattering that must be accounted for when interpreting observations. Moreover, the massive companion star HD 226868 has a strong stellar wind, driven by its high luminosity and surface temperature. This wind is not a gentle breeze. It's a supersonic outflow of charged particles that can interact with the accretion disk and even produce shocks and instabilities. As material from this wind falls toward the black hole, it forms an accretion structure that is neither static nor symmetrical. Instabilities in the flow, clumps in the wind, magnetic fields, and radiation pressure all play a role in shaping how matter moves. These chaotic interactions can lead to variability in X-ray brightness on timescales ranging from milliseconds to days. Scientists track these fluctuations using tools like power spectral density (PSD) analysis and timing studies, which reveal quasi-periodic oscillations (QPOs), signals that may correspond to oscillations in the inner disk or to rotating hot spots orbiting near the ISCO. These QPOs offer a tantalizing glimpse into the region just outside the event horizon, where matter whirls around at near light speed before plunging into the abyss. Another remarkable feature of Cygnus X-1 is its role in the development of our understanding of compact object binaries. It has long served as a touchstone for studies of mass transfer, X-ray variability, disk-corona interactions, and jet formation. For example, during low/hard states, periods when the accretion rate is low, the spectrum becomes dominated by a power law component, often attributed to Compton's scattering of soft photons by a hot, optically thin corona. This corona, which may be a tenuous cloud of electrons above the disk, can reach temperatures of hundreds of keV, creating the high-energy tails seen in the X-ray spectrum. Transitions between low/hard and high/soft states are key to understanding the physics of accretion, and are closely linked to changes in jet activity. The jet in Cygnus X-1, though faint compared to those in blazars or quasars, is persistent. It emits radio waves that can be mapped using very long baseline interferometry, VLBI, revealing a narrow, collimated structure pointing away from the system. These jets carry energy and angular momentum away from the black hole, and while they are not yet fully understood, They are thought to arise from magnetic processes near the black hole's ergosphere, a region where space-time itself is dragged around by the black hole's rotation. Understanding how these jets are launched, collimated, and maintained remains one of the great open questions in astrophysics, and Cygnus X-1 provides an invaluable test case. Beyond its direct scientific importance, Cygnus X-1 has also captured the public imagination. It has inspired books, documentaries, and even songs. The famous Canadian rock band Rush released a track titled Cygnus X-1 Book I, The Voyage, in the late 1970s, blending science fiction with astronomical concepts in a way that brought cosmic ideas into the cultural mainstream. This cultural resonance is no coincidence. Cygnus X-1 was one of the first celestial objects to suggest that black holes were not just theoretical curiosities but real, tangible phenomena observable in our galaxy. The legacy of Cygnus X-1 continues to grow with each new observation and each refinement in our models. As telescopes become more sensitive and computational methods more powerful, we are able to peel back more layers of this complex system. Instruments like NASA's NICER, ESA's XMM Newton, and Japan's Suzaku mission have all contributed critical insights into the system's behavior. Future missions, such as the proposed Athena X-ray Observatory or the Lynx mission, promise even more detailed spectral and timing data, which will allow us to probe the microphysics of accretion and test the limits of general relativity in the strong field regime. Even gravitational wave astronomy may yet play a role in the story of Cygnus X-1. If, in the far future, its massive companion evolves into another compact object, either a neutron star or a second black hole, the system could eventually spiral inward and merge, producing a burst of gravitational waves detectable by next-generation observatories like LISA. While such an event lies millions to billions of years in the future, understanding systems like Cygnus X-1 today lays the groundwork for interpreting such signals when they arise. The very nature of Cygnus X-1 raises some of the deepest questions in modern astrophysics, not only about how black holes form and evolve, but about the very structure of spacetime, the limits of observational precision, and the way matter behaves under the most extreme conditions known to science. As we continue to gaze at Cygnus X-1, we are essentially peering into a laboratory governed by the rules of general relativity and quantum mechanics, both of which collide in complexity near a black hole's event horizon. Delving further into the dynamics of the accretion process in Cygnus X-1, it's important to understand that matter falling into the black hole doesn't plunge in directly. Instead, it spirals inwards through a process driven by angular momentum and viscous forces. The accretion disk formed in this region is incredibly thin and hot, with temperatures in the inner regions reaching millions of degrees Kelvin. This heat causes the disk to emit strongly in the X-ray part of the spectrum. The mechanism behind this emission is predominantly thermal bremsstrahlung, blackbody radiation from the hot gas, and inverse Compton scattering where low-energy photons are upscattered to X-ray energies by high-energy electrons. But within this accretion disk, there is chaos. Turbulent magnetic fields generated by the magnetorotational instability, MRI, differential rotation leading to shear flows, and radiation pressure battling gravity in an uneasy balance. These instabilities can lead to outbursts, sudden changes in brightness, and alterations in spectral states that can be tracked and measured by astronomers in real time. Each spike or dip in the X-ray flux provides a clue, a puzzle piece, that helps build our understanding of the black hole's feeding habits. On top of the accretion disk, we find a mysterious structure known as the corona, a cloud of high-energy electrons that somehow manages to remain suspended above the disk despite gravity's relentless pull. The corona plays a pivotal role in the X-ray spectrum we observe, as it Comptonizes the soft X-ray photons from the disk into a hard X-ray continuum. The size, shape, and temperature of the corona are still under debate. Is it spherical, disk-like, or more of a dynamic, evolving halo? Some models suggest it is connected to the base of the jet, acting as a sort of energy reservoir from which the jet draws power. Jets themselves are among the most spectacular features associated with black holes, and Cygnus X-1's jet, although relatively small by cosmic standards, provides valuable insight into the physics of relativistic outflows. Radio observations have shown that the jet is continuous rather than episodic, hinting at a stable, long-term launching mechanism. This is likely powered by magnetic fields twisting through the rotating accretion disk and tapping into the rotational energy of the black hole itself, a mechanism theorized by Roger Blandford and Roman Znajic in the 1970s. This Blandford-Znajic process is one of the most elegant models in astrophysics, uniting electromagnetism and general relativity in a seamless explanation of how rotating black holes can launch highly collimated jets. When studying Cygnus X-1, astronomers don't rely solely on one wavelength of light. Instead, they use the full electromagnetic spectrum, from radio waves and optical light to X-rays and gamma rays. Multi-wavelength campaigns are essential to get a holistic picture of the system's behavior. For example, the optical light from HD 226868 reveals its temperature, mass, and orbital velocity. Ultraviolet observations trace the behavior of its stellar wind. X-rays uncover the inner accretion disk, and radio maps out the jet's structure. When all these observations are combined, they form a time-resolved, multidimensional tapestry of activity, a moving portrait of one of the most extreme environments in the universe. One of the most intriguing observational challenges has been to measure the precise distance to Cygnus X-1. For decades, estimates varied, introducing uncertainty into the derived physical parameters like the black hole's mass and luminosity. However, in 2011, using very long baseline radio interferometry, a team led by Mark Reed at the Harvard-Smithsonian Center for Astrophysics measured the trigonometric parallax of Cygnus X-1 with extraordinary precision. They found the system to be about 6,070 light-years away, farther than previously thought, which revised upward the estimates of the black hole's mass and the luminosity of its companion star. This distance measurement was pivotal, for it allowed more accurate modeling of the binary system's dynamics. With a better understanding of the orbital period, about 5.6 days, radial velocity, and inclination angle, around 27 degrees to our line of sight, astronomers could refine the mass estimates of both the black hole and the companion star. The black hole's mass has been confirmed to be about 21 solar masses, making it one of the most massive stellar black holes known in the Milky Way. Its companion, the blue supergiant HD 226868, weighs in at around 40 solar masses. This mass asymmetry adds an additional layer of complexity to their interaction, as the black hole's gravity sculpts the wind from the massive star, creating an accretion stream that is far from symmetrical. Indeed, the shape of this accretion stream can be mapped through Doppler tomography, a technique that analyzes the shifting spectral lines of the wind and disk as they move toward or away from us during the orbit. These maps reveal intricate structures, including wind wakes, accretion bulges, and regions of high ionization near the black hole. Each of these features can vary with time, depending on the phase of the orbit and changes in the mass loss rate of the companion star. The supergiant HD 226868 itself is an object of considerable interest. Spectral analysis reveals it to be a spectral type 09.7 IAB star, very hot, very massive, and very luminous. Stars of this type have short lifespans and are prone to instability in their late evolutionary stages. The fact that it's in a close orbit with a black hole complicates its future. Will it eventually lose so much mass to the black hole that it becomes a helium star or even collapses into a neutron star or another black hole? If so, could Cygnus X-1 eventually become a double black hole system? These are not idle questions. They're central to the emerging field of gravitational wave astronomy, where such binaries are expected to be among the most powerful sources. The very notion of a double black hole system originating from a high-mass X-ray binary like Cygnus X-1 raises compelling questions about stellar evolution in binaries. How common are such systems? What fractions survive the supernova phase without being disrupted? What role do metallicity and stellar wind strength play in determining the fate of such pairs? Each of these variables must be fed into population synthesis models that attempt to predict the rates of black hole mergers across cosmic history. Even as we explore Cygnus X-1 from a purely scientific standpoint, we must also acknowledge its symbolic role. It was, after all, one of the first strong candidates for a black hole confirmed not just through indirect inference but through careful, relentless accumulation of evidence across multiple domains. It marked a turning point in astrophysics, a moment when the concept of black holes emerged from mathematical abstraction into the realm of observable reality. Cygnus X-1 helped transform black holes from exotic curiosities to key players in the evolution of galaxies, stars, and cosmic structures. The enduring fascination with Cygnus X-1 continues because it represents the perfect storm of science, mystery, and metaphor. It's a gravitational predator locked in a dance with a luminous victim, a cosmic siphon quietly rewriting the fate of its stellar companion, a machine that converts mass into energy with astonishing efficiency. And despite decades of observation, it still has secrets, hints of turbulence, whisperings of magnetic fury, and shadows that dance just beyond the veil of detectability. Each new generation of astronomers inherits Cygnus X-1 not only as a subject of study but as a benchmark, a crucible in which new ideas about gravity, plasma physics, and stellar dynamics are tested. As we continue to explore it with ever more sophisticated tools, from Earth's surface, from orbital observatories, and someday even from interstellar probes, we will edge closer to understanding what makes this system so uniquely compelling, so eternally enigmatic. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.